In this lesson, we want to review negative exponents and the quotient rule for exponents. So not that long ago in one of our previous review sessions, we reviewed some rules of exponents, right? We talked about the power rules for exponents, and we also talked about the product rule for exponents. And we learned about an exponent of 0, right? We learned that if we took a non-zero number and we raised it to the power of 0, we always end up with the number 1. So today we're going to start out by looking at negative exponents, and then we'll move into the quotient rule for exponents. And you'll see that we're going to need these rules as we start to review radical expressions, okay? So with negative exponents, we're going to look at this using a pattern, and it's the same pattern we use to show how we get a non-zero number raised to the power of 0 to be equal to 1. So I like to work with the number 2. It's nice and small if you're kind of teaching exponents. So if I started out with something like 2 to the first power, we know this is 2. So let's just start here. Then 2 squared is what? Well, I could take 2 and I could multiply it by 2, right? Because I have 2 factors of 2 now, and that would be 4. So to increase the exponent by 1, to go from 1 to 2, I take this number here and I multiply by 2. Let's do that again. If I now go to 2 cubed, what do? I can take this guy right here, this 4, and I can multiply by 2. I can multiply by 2, and I'll get to 8. 4 times 2 is 8, so 2 cubed is 8, okay? Very, very easy to understand that. Now, if we reverse the process, let me kind of erase what I've put here. If I want to decrease my exponent by 1, starting at the 3, if I want to go down to 2, I would take this 8, the result from 2 cubed, and I would basically divide it by 2. So 8 divided by 2 gives me 4. Then if I wanted to go from 2 squared to 2 to the first power, again, I'd start at 4, and I would just divide by 2, right? 4 divided by 2 would give me 2. So following this same pattern, when we get to 2 to the power of 0, right? 1 minus 1 is 0. All I'm going to do is, again, just divide by 2. So 2 divided by 2 gives me 1, okay? This is what we've already learned. Any non-zero number raised to the power of 0 is 1. And the reason it can't be 0 is 0 to the power of 0 would end up being 0 over 0, which is undefined, okay? So as we continue to move down, now we would have 2 to the power of negative 1, right? If I decrease 0 by 1, I get negative 1. So what am I going to do? I'm just going to divide 1 by 2. So this is going to give me 1 divided by 2. You could basically write that as 1/2, okay? 1/2. Now as I keep going, what's going to happen is you're going to see a pattern emerge. So 2 to the power of negative 2 would be what? It would be 1/2 divided by 2. Okay, so divided by 2. So what is 1/2 divided by 2? Using fractions here, we know we would multiply by the reciprocal of this. So dividing by 2 is the same as multiplying by 1/2. So this is basically 1 over 2 squared, right? 1 over 2 squared, or 1/4. But again, I want to write this as 1 over 2 squared because you're going to see something interesting in a minute. Let me erase this. As we go one more time to complete this pattern, I'm going to divide by 2. So 2 to the power of negative 3 is what? It's 1 over, this is 1 over 2 squared times another half. So this exponent here just increases by 1. So this is 1 over 2 cubed. So 1 over 2 cubed, or 1/8. Now, you'll notice that the exponent down here matches the exponent here in terms of absolute value. The exponent here matches the exponent here in terms of absolute value. Again, here and here. So that's going to lead us to the following rule. So for any real number x, as long as x is not equal to 0, if we raise it to the power of negative a, it's equal to 1 over x raised to the power of a. So in layman's terms, basically you take the reciprocal of the base and you make the exponent positive. So in other words, if I wanted 2 to the power of negative 4, I would take the reciprocal of 2, which is 1/2, and I would make the exponent part, which is negative 4 here, positive, okay? So you get 1 over 2 to the 4th power, or just 1/16. Very, very easy rule to implement. So let's take a look at a few easy examples. We have 6 raised to the power of negative 2. So all I want to do is take the reciprocal of the base 6, so that's 1 over 6, and I want to make my exponent positive. Right now it's negative 2. It's just going to be a 2. You could leave this as 1 over 6 squared, or you could say this is 1 over 36. Okay, both answers are correct. Now, one thing I want to show you before we kind of get deeper into the lesson, a common technique to do this is to write this over 1, and then as you drag an exponential expression across a fraction bar, what happens is you leave the base the same, and you change the sign of the exponent. So this would be 6 squared down here, and this would just be a 1 up here, right? And to make that crystal clear, you could start out by just multiplying this by 1, so the 1 is still there in the end. Okay, so that comes in really handy when you're working with something like, let's say I gave you 1 over 2 to the power of negative 3. Well, instead of going through kind of a lot of mess there, you can just drag this up here and say this is 2, change the sign of the exponent to positive, so this is 2 cubed, okay? If you wanted to do this kind of the long way, what you would do is you would say this is 1 over 1 divided by, you would have 2 raised to the power of negative 3 is 1 over 2 cubed. And so now what you would do is you're dividing 1 over 1 by 1 over 2 cubed, right? So it would be 1 times the reciprocal of this, which is 2 cubed, which equals 2 cubed, okay? So a very, very lengthy process when you have this scenario where this guy's in the denominator. So it's just easier to drag it across the fraction bar, keep the base the same, change the sign of the exponent. All right, so let's look at another one. So we have 3 to the power of negative 4. Again, all I want to do is take the reciprocal of the base, so 1 over 3, change the sign of negative 4 to positive 4, and I have 1 over 3 to the 4th power, or you could say 1 over 81. Suppose we had something like x to the power of negative z. How could we write this without a negative exponent? Take the reciprocal of the base, so 1 over x, and this would be raised to the power of positive z, okay? So this is 1 over x to the power of z. All right, let's go ahead and take a look at another one. So we have 3x to the power of negative 5, y to the power of negative 2. This is over. We have z to the power of negative 4, q to the 8th power. So if I wanted to simplify this or write it without any negative exponents, what I could do is I could leave 3 unchanged in the numerator. I have this x to the power of negative 5. How could I write that without a negative exponent? Well, I could just drag this across the fraction bar. Keep x the same. So again, keep the base part the same. Change the sign of the exponent. So right now it's a negative 5. We would make this a positive 5. We're going to do the same thing for y raised to the power of negative 2. Again, just drag it across the fraction bar. This becomes y raised to the power of what? Change the sign from negative to positive. So you get y squared down there. Now in terms of my denominator here, I have z raised to the power of negative 4. So if I drag this into the numerator, same thing applies, right? If you cross the fraction bar, you just keep the base the same. So z stays the same. Change the sign of the exponent. So from negative 4, it will become positive 4. And then my q to the 8th power here, I don't need to do anything with that other than just leave it in the denominator. It does not currently have a negative exponent, so I don't need to do anything with it. So I end up with 3z to the 4th power over, we have x to the 5th power, y squared, q to the 8th power. All right, for the next one we have inside of parentheses 2 times x raised to the power of negative 2 times z raised to the power of negative 1 times q. So this whole thing inside of parentheses is raised to the power of negative 3. Then this is all over 3n to the 4th power. So to simplify here, I'm going to use my power to power rule. So each part here is going to be raised to the power of negative 3. So I would have 2 raised to the power of negative 3. I would have x to the power of negative 2 raised to the power of negative 3. So what do I do there? I keep my base x the same. I multiply exponents. Negative 2 times negative 3 is positive 6. Z to the power of negative 1 is raised to the power of negative 3. Keep z the same. Multiply negative 1 times negative 3. That's 3. And then q is raised to the power of negative 3. Okay? And this is over 3n to the 4th power. Okay, so what do we have here that has a negative exponent? So we have this guy and we have this guy. So let's just drag those across the fraction bar. So if I take 2 to the power of negative 3 and I place it in the denominator, 2 stays the same and the exponent changes to positive 3. X to the 6th power, I leave that in the numerator. Z cubed, I leave that in the numerator. This guy, q to the power of negative 3, drag it across. So q comes down here. The exponent changes from negative to positive. So I get q cubed, and then I have 3n to the 4th power. So let's clean this up. We know 2 cubed is 8, and 8 times 3 is 24. So I'm going to write this as x to the 6th power, z cubed, over, I'm going to have 24, and then times q cubed, and then times n to the 4th power. Okay, that would be my answer. All right, let's take a look at another one. So we have x squared, y to the power of negative 1, z to the 4th, inside of parentheses, and this is raised to the power of negative 7. So again, I'm going to use my power to power rule. So x squared is raised to the power of negative 7. X stays the same. 2 times negative 7 is negative 14. Y to the power of negative 1 is raised to the power of negative 7. Y stays the same. Negative 1 times negative 7 is 7. And then z to the 4th power is raised to the power of negative 7. Z stays the same. 4 times negative 7 is negative 28. So if I want to deal with this guy right here with a negative exponent and this guy right here, y to the 7th power just stays in the numerator. X to the power of negative 14, I'm just going to drag the x down here into the denominator. Negative 14 becomes positive 14. I'm going to drag this z down here into the denominator. Negative 28 becomes positive 28. So my answer here is y to the 7th power over x to the 14th power, z to the 28th power. All right, so now that we have a great understanding of how to work with negative exponents, let's move on and talk about the quotient rule for exponents. This is very, very simple. Basically, when we divide with like bases, we keep the base the same and we subtract the exponent in the denominator away from the exponent in the numerator. Okay? Very important there that you follow that direction. When we looked at the product rule for exponents, it didn't matter how you add it because addition it's irrelevant, right? The commutative property tells me if I add 2 plus 3 or 3 plus 2, I get the same result. Subtraction is not commutative, so you got to make sure you do this in the right order. So if I have something like x to the power of a over x to the power of b, this is equal to x raised to the power of a minus b. So why is that the case? Well, let's look at an example. So let's look at this 2 to the 7th power over 2 cubed. So following our rule, the base 2 would stay the same, and I would subtract 3, the exponent in the denominator, away from 7, the exponent in the numerator. So this would be 2 raised to the power of 7 minus 3. We know that 7 minus 3 is 4, so this would be 2 to the 4th power, or 16 if you wanted to write that. Now, let's think about why this is the case. What is 2 to the 7th power? It's 7 factors of 2. 2 times 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6, 7 factors of 2. Okay? What is 2 cubed? 2 times 2 times 2. Okay. Well, if I write these over each other, like this, it is very clear that I can basically cancel 3 of these guys, right? Because I can cancel this with this, this with this, and this with this. So I've removed 3 factors of 2. What did I do here? I started with 7 and I removed 3 and I ended up with 4. Same thing here. Okay, so that's all you're really doing. And it works either way. If I wrote, let's say 2 to the 3rd power, or 2 cubed, over 2 to the 5th power. The exponent in the denominator is larger here, so I have more factors of 2 in the denominator. It's still going to work. So 2 times 2 times 2 times 2 times 2. This is 2 times 2 times 2. So following this, this cancels, this cancels, this cancels. I'm basically going to have 1 over 2 squared, or 1/4, right? If I follow my formula, what do I have? Base stays the same. Subtract the exponent in the denominator, which is 5, away from the exponent in the numerator, which is 3. So 3 minus 5 is negative 2. So this equals 2 to the power of negative 2. We all know at this point that this is what? Reciprocal of the base, which is 1 over 2. Make the exponent positive, so it's 1 over 2 squared. It's exactly what we have here, okay? So it works the same way, whether you have a larger number of factors in the denominator or a larger number of factors in the numerator. You just follow the pattern. All right, let's go ahead and take a look at an example. So we have 5 squared times x squared times y to the 4th power. And this is over. We have 5 cubed times x to the 9th power times y cubed. So if we wanted to simplify this, we would look for like bases. We have 5 squared over 5 cubed. So 5 would stay the same. And then again, I would subtract the exponent in the denominator, so the 3, away from the exponent in the numerator, which is a 2. So I would have 5 raised to the power of 2 minus 3. And we know that's negative 1, but let's replace that in a minute. Let's just keep going for now. So then we have x squared over x to the 9th power. So x stays the same. And then we're going to raise this to the power of what? It's this guy, the 9, that's being subtracted away from this guy, the 2. So we have 2 minus 9. We know that's negative 7, but again, we'll do that in a minute. Then we have y to the 4th power over y cubed. So y stays the same. And then we want to do 4 minus 3, right? Because this is the guy in the denominator. This is the guy in the numerator. You want the guy in the denominator, which is 3, to be subtracted away from the guy in the numerator, which is 4. So this is 4 minus 3. So this ends up being what? Again, 2 minus 3 is negative 1, so 5 to the power of negative 1. You have x raised to the power of 2 minus 9, so x raised to the power of what? That's negative 7. And then y raised to the power of 4 minus 3, which is just y. So now, if I think about how to simplify this, if I want to get rid of 5 raised to the power of negative 1, that's what? It's just 1/5. But again, a simpler way to do that is just to set up a little fraction bar. Y stays in the numerator because it does not have a negative exponent. This guy right here, if I drag it into the denominator, the 5 part stays the same. The exponent changes from negative 1 to positive 1. And a positive 1 as an exponent is implied, right? So you don't need to write it. Then I have x to the power of negative 7. Again, if I drag this into the denominator, I'm going to have my x part stay the same. My negative 7 will change to positive 7. So we basically have y over 5x to the 7th power. All right, let's take a look at one more. So we have 7 that's multiplied by x to the power of negative 2 times y cubed times z to the power of negative 4. This is over. We have inside of parentheses x multiplied by y to the 4th power multiplied by z squared. This is all raised to the power of negative 2. So the first thing I want to do is kind of simplify down here. So let me just rewrite this. I have 7x to the power of negative 2, y cubed, z to the power of negative 4. Down here, I got to use my power to power rule. So x would be raised to the power of negative 2. Y would be raised to the power of what? Keep that the same. 4 times negative 2 is negative 8. Z would stay the same. Multiply 2 times negative 2, that's negative 4. So now I'm just looking at, I have a 7 up here. Nothing's going to change with that. I have x to the power of negative 2 over x to the power of negative 2. What is that? That's just 1, right? If I have x to the power of negative 2 over x to the power of negative 2, same thing over itself is going to be 1. Okay, unless it's 0, and we're assuming that x is not 0 here. So I can show you this also by saying keep x the same. Take this guy right here, negative 2, and subtract it away from negative 2. What is negative 2 minus a negative 2? This is negative 2 plus 2, which is 0. X to the power of 0 is 1. Okay, so that guy's canceled. So you can cancel this. Same thing for the z. You have z to the power of negative 4, z to the power of negative 4, cancel it. So all I have left is a y raised to the power of 3 over a y raised to the power of negative 8. So you're going to subtract this guy away from this guy, okay? So if I subtract negative 8 away from 3, so 3 minus a negative 8, be careful there, you want to minus the negative 8. This is the same thing as 3 plus 8, which is 11, okay? So you get 7y to the 11th power. Now, another way you could have done this, you could have had 7 up here. You could drag the y up. So you could have y cubed. If you drag the y down here up into the numerator, it's y. The exponent changes from negative 8 to 8. Then you could just use your product rule, right, for exponents. So you have 7y raised to the power of 3 plus 8, which is 11. Okay. So a lot of different ways to kind of do the same thing, whatever you're more comfortable with. If you like dragging things across the fraction bar, cool. Just keep the base the same, change the sign of the exponent. Okay, if it goes across from numerator to denominator or denominator to numerator, you also have the method of just taking the reciprocal of the base and making the exponent positive. So either way you want to do it. In this lesson, we want to review rational exponents. So in this section that we're in currently, we're exclusively going to be reviewing radical expressions. So it's very important to understand how to convert between the radical notation and kind of the exponential notation that's involved when you work with radicals. So we're going to kind of start out with this first rule, and then we're going to work through some examples. We have that the nth root of x is equal to x raised to the power of 1 over n. And basically what we're doing here is we're taking this index here and we are placing it in the denominator of this fractional exponent. So you have a 1 over n, where again, n is the index of your radical. So if we look at something pretty easy like a square root, if we have the square root of x, we can write this as x raised to the power of 1/2. Remember, when we work with square roots, there's an implied index of 2. We don't write it, but it's there, right? So this guy's a 2. That means this guy's going to be a 2, right? So if I wanted to prove this mathematically, that the square root of x is equal to x raised to the power of 1/2, how could I do that? Well, we know that the square root of x multiplied by the square root of x is equal to x, right? And that's true for any non-negative real number x. So if I had something like the square root of 3 multiplied by the square root of 3, this would give me 3, right? If I wanted to write this in exponential form, instead of writing the square root of x like this, I would just write x to the power of 1/2, and I would multiply it by x to the power of 1/2, and I would say this is equal to what? Well, I would use my product rule for exponents. The base is the same. I have x, I have x. So I'm going to put an x here, and then I'm going to add my exponents. So I have a 1/2 plus another 1/2. What's that going to give me? I know that the denominator there is a 2 in each case, so I have a common denominator already. So I just need to add the numerators. 1 plus 1 is 2. If I had 2 over 2, it would just be 1. So this is x to the first power, or just x. So you can see that whether you write this in kind of radical notation by putting the square root symbol, or writing this with exponential notation where you have a 1/2 as the exponent, it's the same exact thing mathematically. So as an example here, we showed the square root of 3 times the square root of 3 was 3. It would also be true that 3 to the 1/2 power times 3 to the 1/2 power is equal to 3. Again, same thing here. Base is the same, so 3 would stay the same. You would add the exponent 1/2 to the exponent 1/2. You would get 1. 3 to the first power is just 3. So let's practice a few easy examples. If I had something like the square root of 2, how could I write this using an exponent? Well, again, I could just take this guy right here, this 2. That's going to be the base for my exponential expression. The index here, which is an implied 2, would be the denominator of my fractional exponent. So I would have a 1 over a 2, or just a 1/2. But it's easy to remember when you have the square root of something, it's just raised to the 1/2 power. If you have the cube root of something, right, the index is 3, it's raised to the 1/3 power. If you have the fourth root, it's raised to the 1/4 power. So on and so forth. So square root of 5x, again, 5x, the whole thing here, the 5 and the x, is going to be raised to the power of 1/2. You know from working with exponents that you could also write this as 5 to the power of 1/2 times x to the power of 1/2. So all of these mean the same thing. We have 5x as a radicand. We're taking the square root of 5x. All right, what about something like this? We have the square root of 3x plus 5. So we have to be careful here. This whole thing would be inside of parentheses, and we'd raise it to the 1/2 power. Now, can I distribute like I just did in the last example? No. You cannot distribute exponents over a sum. I've probably said this in like 5 videos already. Very important that you don't do something like this. Please don't say this is 3x to the power of 1/2 plus 5 to the power of 1/2. That is absolutely wrong. This is wrong. Please don't do this. Okay, it's a very common mistake, and I'll just keep mentioning it till it gets through your head. Okay, you can't do that. You can only do that with multiplication. If we had something like, let's say, the square root of 3x multiplied by 5y, something like that. And of course, this could be simplified and we could just put the square root of 15xy. But in this case, I could write this as what? Inside of parentheses, 15xy raised to the power of 1/2. Because this is multiplication here, 15 is multiplied by x, which is multiplied by y, you can use your rules for exponents. So the 1/2 can actually be distributed there. So it can be applied to each of these. So 15 would be raised to the power of 1/2. X would be raised to the power of 1/2. And y would be raised to the power of 1/2. So that's okay. That's legal because it's multiplication. But when you have a sum involved like this, you can't do it. Okay, so make sure you understand that. So writing this with a fractional exponent, or using rational exponents if you want to say that, you get 3x plus 5 inside of parentheses. The whole thing's raised to the power of 1/2. All right, so again, if you're working with higher level roots, it's the same thing, okay? So if I have the cube root of x, this is x raised to the 1/3 power. This index here is always going to match this denominator here, okay? So if I had the cube root of 2, I could just write this as 2 to the power of 1/3. Very, very simple. What if I had something like this? I have the cube root of 12x squared y squared z. Notice how it's all multiplication here, okay? So I could write this as 12x squared y squared z inside of parentheses and raise this guy to the 1/3 power. And again, because it's all multiplication here, there's no sum involved, I can put 12 to the power of 1/3. I can put x squared to the power of 1/3. So power to power rule, that would be x to the 2/3 power. And we'll talk about what that means in a minute. Then we would have y squared raised to the 1/3 power. So power to power rule, 2 times 1/3 is 2/3. And then you'd have z raised to the power of 1/3, okay? All right, let's evaluate a few of these. So we have 64 raised to the 1/3 power. So to do this, you could either realize you're taking the cube root of something, or you can convert it into radical notation. A lot of people will convert to radical notation to evaluate. So we'll just go ahead and convert this to the cube root of 64 like this. I know off the top of my head that the cube root of 64 is 4. But if you didn't know that, again, you could just factor 64. Most of you would just use a calculator, which is perfectly acceptable in today's age. But if you wanted to do this without a calculator, you would say, okay, 64, I know that's 4 times 16. 4 is 2 times 2. 16 is what? It's 4 times 4. And 4 is 2 times 2. So you can see that if you wanted a number that was multiplied by itself 3 times that gave you 64, you would be looking for 4, right? You have 4 times 4 times 4. So again, the cube root of this would be 4. Okay, pretty easy. What about 625 raised to the power of 1/4? Well, again, if this part right here is your denominator, that's the index of the radical. Okay, so 625 raised to the power of 1/4 is the 4th root of 625. Again, another common problem. So I know off the top of my head this is 5. Many years of working with this. But again, if you didn't, punch it up on a calculator as 625 raised to the power of 1/4. Or you could do the 4th root of 625. Same answer, you get 5. Or again, go ahead and just factor this guy. This, we can say, ends in a 5. So it would be 5 times 125. 125 is 25 times 5. 25 is 5 times 5, okay? So what number multiplied by itself 4 times gives me the radicand of 625? Well, 5, right? I've got 1, 2, 3, 4 of these guys. So I can just answer this and say this is going to be 5. Okay, pretty simple. So if we have the nth root of x and it's raised to the power of m, in exponential notation, we can write this as x raised to the power of m over n, okay? All you're basically doing is just using your power to power rule. If this guy right here is x raised to the power of 1 over n, okay, so we already defined that. If this is now raised to the power of m, again, just using the power to power rule, this is x raised to the power of m times 1 over n, which is just m over n, okay? Very easy. Now, because of the commutative property of multiplication, you're going to see that it doesn't actually matter if you have the nth root of x to the mth power, or if you have the nth root of x and this thing is raised to the power of m. Why doesn't it matter? Well, in this case right here, what do I have? I end up with x to the power of m, and this is being raised to the power of 1 over n. Well, if I use my power to power rule, I get x raised to the power of m over n. Same thing as up here, same thing as we're going to get here. right? We already know this scenario because we've already shown that this is equal to x raised to the power of m over n. But again, it's the same thing because of the commutative property of multiplication. You can multiply in any order, it's not going to change. Typically, this is how you'd want to do it though, because you want to work with a smaller value. So let me show you that real quick. So let's say you had 4 raised to the 3/2 power, and you're asked to evaluate this. You want to know what it is. So you can either do 4 cubed and then raise that to the power of 1/2, or you can also do 4 raised to the power of 1/2, and then you can cube that. If you use your power to power rule here, either way you end up with 4 raised to the power of 3/2, right? 1/2 times 3 this way, or 3 times 1/2 that way, you end up with 3/2, right? Again, commutative property of multiplication. So doing it this way, 4 cubed is 64. If I take the square root of 64, or again, raise this to the 1/2 power, I get 8. But notice I had to work with a really big number there. I mean, 64 isn't a really big number, but it's a bigger number than I would work with here. In this scenario, the square root of 4 is 2. If I cube 2, I also get 8. It's the same result, but this guy allowed me to work with a smaller number, and therefore in a lot of cases it's less tedious and it's just easier. So for myself, this method is preferred. Okay, this is my preferred method. But again, in math, there's a lot of different ways to do things. So whichever way you want to do it, it doesn't matter because you'll get the same result either way. All right, let's go ahead and take a look at negative 27 raised to the power of 5/3. So essentially, I'm going to write this as negative 27. This whole thing, I'm going to include parentheses here because I have a negative involved. This is going to be raised to the 1/3 power. And then I'm going to raise this, I'll just use brackets here, to the power of 5. So to write this more simply, or in a more recognizable form, I'm going to write the cube root of negative 27, and then I'll raise this to the 5th power. So most of you know the cube root of negative 27 would be negative 3, right? So negative 3. Again, that's because negative 3 times negative 3 is 9. 9 times negative 3 is negative 27. Then we'd raise this to the 5th power, and that would give me what? Negative 243. Negative 3 times negative 3 is 9. 9 times negative 3 is negative 27. Negative 27 times negative 3 is 81. And then 81 times negative 3 is negative 243. All right, what about something like 16 to the power of negative 3/4? Again, what I'm going to do, I'm going to take 16, and I'm going to start out by raising it to the 1/4 power. And then I'm going to raise this guy to the power of negative 3. Okay? So we know how to work with negative exponents. We'll get to that in a second. First and foremost, let's just do this as the 4th root, right? Because this guy's a 4, of 16. And then again, this guy's raised to the power of negative 3. So the 4th root of 16 is 2, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So this is 2 raised to the power of negative 3, which again is take the reciprocal of the base. So this becomes 1 over 2. Make this guy positive. So this is 3. So this ends up being 1 over 8 because 2 cubed is 8. Now, there's another way you could have done that. Let's erase everything. We know that when we work with a negative exponent, we take the reciprocal of the base and we make the exponent positive. So I could start out, because I have a negative exponent here, writing this as 1 over 16 raised to the power of 3/4. Okay, I could do that to start. So this is 1 over the 4th root of 16, which is going to be cubed. So this is 1 over 2 cubed. So this is 1 over 8. Okay, that's another way to do it. But again, in all of mathematics, you're going to have many different ways to do things. You pick one that works for you. You pick one that you like and that you can remember, and you do it that way. All right, so let's look at a few examples here. And these are just going to be examples that help you kind of bring your knowledge of exponents together. It's always good to get some practice with exponents so that kind of later on in the course when we look at some really challenging materials, you don't get tripped up on stuff that's trivial like exponents. So if we have something like 2 raised to the power of negative 2 times x raised to the power of negative 3/4 times y raised to the power of negative 5/8, and this is over, x raised to the power of 3/4 times y raised to the power of negative 1/2. So this whole thing's raised to the power of negative 3. So I'm going to start by just using my power to power rule and everything. Notice that there's no addition involved. This is all multiplication. So I'm going to have 2 raised to the power of negative 2 raised to the power of negative 3. 2 stays the same. Multiply exponents. Negative 2 times negative 3 is positive 6. Then I have x, which stays the same. Negative 3/4 times negative 3. would be positive 9/4. Y would stay the same. Negative 5/8 times negative 3 would be positive 15/8. This is over. Same thing applies in the denominator. We have x there that stays the same. 3/4 times negative 3 would be negative 9/4. And then you have a y, and then negative 1/2 times negative 3 would be positive 3/2. So now that we've done that, let's go through and use the quotient rule for exponents, which we talked about in the last lesson, and see what we can simplify. So we know that 2 to the 6th power is going to be 64, right? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and then 32 times 2 is 64. You can leave that as 2 to the 6th power or just put 64. Doesn't matter. Then you have x and x, so same base. Let's just write it. You want the exponent in the denominator here, which is negative 9/4, to be subtracted away from the exponent in the numerator, which is 9/4. So 9/4 minus a negative 9/4. Okay? We know if we subtract away a negative, we're adding a positive. So you might as well just put plus 9/4. So 9 plus 9 would give me 18, so I would have 18/4. So 18/4. So we can simplify this. 18 and 4 both have a common factor of 2. This would be 9/2. Okay, so 9/2. Then next, I have my y. So I have y that I'm going to write here. Again, this guy right here is going to be subtracted away from this guy right here. So you would have 15/8 minus 3/2. You got to get a common denominator going. So I'm going to multiply this by 4/4. So this would be a 12/8, right? So I'm going to write this as 12/8. 15 minus 12 is 3, so this would be 3/8. Okay. Now let's take a look at one more here. So we have 4x raised to the power of 5/3 multiplied by the quantity x raised to the power of negative 2/3 minus 8x raised to the power of negative 5/3. So a lot of you might get confused with this problem. I have students that I've tutored in the past, and they look at this problem, they go, I can't distribute that because you said you can't distribute when there's a sum or a subtraction. Well, no, that's when you're talking about exponents, right? I can still distribute this guy. This is multiplication here. I'm multiplying this by this difference, or if you wanted to write this as plus negative, you could say by this sum, right? So that's okay. It's perfectly legal. It's just when you have something like, let's say, x squared plus y squared, and you have an exponent like 1/3, you can't distribute the exponent, okay? That's what you can't do. But I can still distribute this. So what would I have? Well, I'm going to just work with this as 4, nothing to combine with that. X to the 5/3 power multiplied by x to the negative 2/3 power. X stays the same. You would add the exponents. So what is 5/3 plus negative 2/3? 5 plus negative 2, or 5 minus 2 is 3. 3/3 is what you have. 3/3 is just 1, so this is just 4x. Then we have plus, I'm going to just treat this as negative 8x to the power of negative 5/3. So 4 times negative 8 is negative 32. So I can just go ahead and write minus if I want. So minus 32. Then I know I'll have an x. And what will my exponent be? You have 5/3 plus negative 5/3. So 5/3 plus negative 5/3. Or basically 5/3 minus 5/3, that's 0. So what is x to the power of 0? It's 1. So I can just say this is 4x minus 32 as my answer. Some of you will like to factor that and say this is 4 times the quantity x minus 8. That's fine as well. So either of these answers would be fine. In this lesson, we want to review radical expressions. So in the last lesson, we reviewed rational exponents, which are also known as fractional exponents. Now I want you to recall these allow us to convert between radical notation and exponential notation. So what we want to do is just quickly recap that process because we're going to need that operation for our lesson today. So if we have something like the nth root of a, we should recall that we can write this in exponential form by basically taking the radicand a and writing that as the base of our exponential expression. And so a will be raised to the power of 1 over the index. In this case, the index is n, so 1 over n. So if I had something like, let's say, the square root of 4, this has an implied index of a 2. So essentially, in exponential notation, I just take this 4, and I say it's raised to the power of 1 over, again, the index is 2, so 1 over 2, or 1/2. So we know that taking the square root of a number is like raising it to the power of 1/2. Similarly, if we take the cube root of a number, it's like raising it to the power of 1/3. So something like, let's say the cube root of 27, this would be equal to, the 27 here is the base of the exponent, and it's raised to the power of 1/3. Now, we have another rule which we're going to rely on heavily throughout our course. If you have the nth root of a, and let's say a is raised to a power now. So a is raised to the power of m. This is equal to, this part's the same. We're just going to have a raised to the power of m over n. So everything's the same except for the fact that you have an m in the numerator now over your n, your index, in the denominator. Now you might also see this written in a different form. You could also say this is the nth root. Let me make that n a little better. So the nth root of a, and this whole thing is raised to the power of m. And essentially because of the power to power rule, you could really write this as a raised to the power of m over n as well. But essentially for this lesson, we're going to deal with this scenario. So we don't really need to worry about this. We just want to reference it maybe later on if it comes up. So we can use this rule to kind of simplify here. I want you to realize that 4 is nothing more than 2 squared, right? So we know the square root of 4 is 2 because 2 squared is 4. But to simplify this using exponents, we can say the square root of 2 squared like this, and we'll go ahead and say this is equal to, we have 2, which will be raised to the power of 2 over 2, which is basically 2 raised to the first power. So I want you to realize that in most cases, you're going to be able to cancel an exponent here with an index here. We'll see later on in the lesson that when you have a negative involved there and you have an even index, you need to kind of think about what's going on first. But in general, you can just cancel between here and here if your number here is non-negative, okay? So we'll talk about the exception later on in the lesson. So as this one goes, we have the cube root of 27. We know 27 is 3 cubed, so I could write this as the cube root of 3 cubed. And again, if I wanted to, I could cancel this with this, but I'm going to show that process with exponents. So I can say this is 3 raised to the power of 3 over 3. So this exponent over this index, and this is equal to 3 over 3 is 1, so 3 to the first power, or just 3, right? And here I could just really write this as 2. All right, so the purpose of this lesson is to give a basic overview of radical expressions. Most of you, or if not all of you, understand how to take the square root, the cube root, the fourth root of some number. But it's important to kind of go back and make sure you understand all the vocabulary and all the different scenarios that we're going to encounter throughout the course. So we'll start with something very basic. We're going to show the parts of a radical. So if you have the nth root of a, the n right here is known as the index. And for a square root, the index is left blank. So if you have a square root, it's implied to be a 2, right? So something like, again, the square root of 4. You don't show a visible index, but it's known or understood to be a 2. But if I have a cube root, a fourth root, a fifth root, some higher level root, I need to make it clear that I have that level, and so I want to put a visible number there. So if I have the cube root of 8, I want to make sure to put a 3 there to identify that this is a cube root, okay? So very important that you do that. Then this guy right here, this number or variable or expression that's underneath the radical symbol is known as a radicand. And then the symbol itself is just called a radical symbol. Radical symbol, okay? Then when we talk about the whole thing together, it's just known as a radical. So when I say a radical, I'm talking about all parts of this together. So what does a radical allow us to do? Well, we know about taking a number to a power. And essentially, when we have a radical expression, it's reversing the operation of raising to a power. So just like addition and subtraction are inverses, multiplication and division are inverses, you have radicals that are inverses with kind of raising to a power. So it basically asks the question, what number raised to the index is equal to our radicand? So in this case, we have the square root of 49. So I'm going to put a visible index of 2 here just for our demonstration purposes. But again, you don't need that. And essentially, I'm asking what number, so let me write this out, what number raised to the power of the index, and the index in this case is 2. So what number raised to the power of 2 gives us the radicand, which in this case is 49. So that's the question we're asking each time. If I had the cube root of 8 as another example, I would just say what number raised to the power of 3, because my index is a 3, gives us the radicand is 8. Okay? If I had the fourth root of, let's say, 625. So it would be what number raised to the power of 4 gives us the radicand of 625, so on and so forth. So it's a very simple process to understand. Now, how do I go about figuring this out? Well, if I don't have a calculator, I need to factor. 49 happens to be a perfect square, so it's built from the product of a rational number times itself. And we'll talk more about the definition of a perfect square in a minute, but essentially when you factor 49, you only get 7 times 7, or you also get negative 7 times negative 7. So to answer this question, what number raised to the power of 2 gives us 49? It's 7, or also negative 7. When we work with radicals, and we have an even root, so a root that's a square root, a fourth root, a sixth root, so on and so forth, we're going to get two different roots. You're going to get a positive or principal root, and then also a negative root. So this guy right here, the square root of 49 written like this would just be 7, because this is the principal or positive square root of 49. Then, to notate the negative square root of 49, I just put a negative out in front. So I would say the negative square root of 49, and this equals negative 7. So for this guy, it's asking, what positive number squared gives me 49? That's 7, right? Because 7 squared is 49. This guy's asking, what negative number squared gives us 49? In this case, that's negative 7, because negative 7 inside of parentheses squared is positive 49. And then we have a shorthand to include both of these in one. So we put plus or minus like this, the square root of 49. This just means to give me the principal square root of 49, which is 7, and the negative square root of 49, which is negative 7. So I'm going to write this as plus or minus 7. Okay, so very, very compact notation there, and something we're going to use throughout the course. So what if I got something like the square root of 144, and I wanted to figure out what that was without using a calculator? What could I do? So most of you know that 144 is also a perfect square. It's 12 times 12. But if you didn't know that, you could just factor the number. So 144, you just use your divisibility rules. So this guy ends with 44. 44 is divisible by 4, right? 44 divided by 4 is 11. So that tells me the number 144 is divisible by 4. So what would it be? It would be 4 times 36. 4 is 2 times 2. 2 is a prime number, so let's just circle those. And then 36 is 9 times 4. 4 again is 2 times 2. 2 is a prime number, so let's circle those. And then we know that 9 is 3 times 3. And let me make that better. And we'll circle these 3's here. So we can see that we have 2 times 2 times 2 times 2, where you could really say you have 2 squared times 2 squared again times 3 squared. And I did this to where each number there had an exponent of 2 because we're looking for something that's squared. So now we can use our rules of exponents to write this as 2 times 2 times 3 being squared. 2 times 2 is 4, 4 times 3 is 12, so this is 12 squared. So that's one way to find the square root of a number if you don't have a calculator. It's unrealistic at this point in time to not ever have a calculator because we all have these phones in our pockets that can basically do anything. But in case you wanted to know how to do it, that's what you would do. So we would say the principal square root of 144 is 12. If I was asked for the negative square root of 144, that would just be negative 12. What about something like the negative fourth root of 625? Well, again, I'm looking for a negative number that when raised to the fourth power gives me the radicand of 625. So I know that an even number of negative factors gives me a positive. So that part would be taken care of. I know this would just be a negative. So 625, if I factored that, it ends in 5. So it would be 125 times 5. 125 is 25 times 5. And 25 is 5 times 5. So we can see this is 5 to the fourth power to get us to 625. But also negative 5 to the fourth power would be 625 as well. Because you would have negative 5 times negative 5 times negative 5 times negative 5. So an even number of negative factors would give me a positive product. Okay? So the negative fourth root of 625 is negative 5. If you got asked for the principal fourth root of 625, that would be positive 5. All right, so when we work with odd roots, like a cube root, a fifth root, a seventh root, so on and so forth, we don't need to worry about having a plus or minus there. When you have an odd number of negative factors, you get a negative result. So there's not going to be two roots here. So if I have something like the cube root of negative 64, we would just think about what number cubed, what number raised to the third power gives us negative 64. Well, I know it's negative, right? Because negative times negative times negative would give me a negative. So I just need to work out 64 and think about the factors there. I know it's divisible by 4. It's 4 times 16. And I know 16 is 4 times 4. Now I can go through and say this is 2 times 2, and this is 2 times 2, and this is 2 times 2. But for the purposes of what we're doing, we've already found that 4 to the third power, or 4 cubed, is 64. So the cube root of negative 64 is just negative 4. What about something like the fifth root of negative 243? Well, for this guy, again, I'm looking for what number raised to the fifth power is going to give me negative 243. So think about the fact that this will be negative, and to factor 243, you've got 81 times 3. You've got 9 times 9, and this is 3 times 3. All right, and this is 3 times 3. So you've got 1, 2, 3, 4, 5 factors of 3. 243 is 3 to the fifth power, right? So the fifth root of negative 243 is negative 3. So when we work with radicals, we're basically going to have 3 different scenarios. So we should recall that our real number system breaks up numbers into either rational numbers or irrational numbers. So when you work with radicals, you're either going to have a value that represents a rational number, it could represent an irrational number, or it could represent something that is not a real number. So we'll get to the last part of that in a moment. For right now, let's talk about how you can tell if you have a rational number or an irrational number. So you've probably heard the term perfect square, perfect cube, perfect fourth, so on and so forth. So what is a perfect square? A perfect square is a number whose square root is a rational number. So if we went through kind of the first few whole numbers, let's say we had 1 squared, this is 1, 2 squared, this is 4, 3 squared, this is 9. Let's just skip a few and go to 10. 10 squared is 100. Let's skip a few more and go to 20. 20 squared is 400. So I would recommend you memorize from 1 all the way to 20, squaring those numbers. What's the result? It's something you're going to need to go back and forth with. But essentially, each of these results here are perfect squares, right? So if you think about the square root of 1, it's 1, right? It's a rational number. The square root of 4 is 2, a rational number. The square root of 9 is 3, a rational number. The square root of 100 is 10, a rational number. And the square root of 400 is 20, a rational number. So these are perfect squares because when I take the square root, I get a rational number. So if I have something like the square root of, let's say, 400, this represents the rational number 20. Okay, you could also have a scenario where you have a fraction that's a perfect square, right? So it doesn't have to be limited to a whole number or an integer. You could have something like the number 1/4. This is a perfect square because the square root of it is 1/2. Okay, so the square root of 1/4 is a rational number 1/2, so 1/4 is a perfect square. Now, you could expand this definition to having a perfect cube or a perfect fourth, whatever it is. For a perfect cube, you think about cubing a number. 1 cubed is 1, so 1's a perfect cube. 2 cubed is 8, so 8's a perfect cube. 3 cubed is 27, so 27's a perfect cube, so on and so forth. So if the number, when I take the cube root of it, gives me a rational number, it's a perfect cube. If a number, when I take the fourth root of it, gives me a rational number, it's a perfect fourth, right? So on and so forth. Now, if I'm taking a square root of a number and that number is not a perfect square, I have a radical that represents an irrational number. So, for example, 5 is not a perfect square. There's no rational number that I can square to get 5. So if I take the square root of 5, this represents an irrational number. This is irrational. And you can punch that up on a calculator and you're going to get a nasty decimal. And it's a decimal that does not terminate and it does not repeat the same pattern forever. So at some point, because you're limited in space, your calculator is either going to truncate or it's going to round, right? It's going to do one of the two, and it's going to give you an approximation of the square root of 5, but it won't actually be equal. And the way you can prove that to yourself is you can take the number they give you and you can square it and you won't exactly get 5. You'll just get something that's close. Then the same thing goes if I take the cube root of something that's not a perfect cube. So let's say I took the cube root of 12. 12 is not a perfect cube. There's no rational number that I can cube to get 12, okay? So that means if I take the cube root of that, it's going to be irrational, okay? So the last scenario you're going to deal with is a radical that represents something that is not real. So we know that we have imaginary numbers and the complex number system that we can use to deal with this. And we'll talk about that in a few lessons. For right now, we just need to understand this concept because it will come up a lot throughout our course. So if we take the square root of a negative number or an even root of a negative number, we get a problem. An even number of negative factors always gives me a positive. So if I try to take the square root of negative 25, I'm basically asking the question, what number squared or what number multiplied by itself gives me a product of negative 25? Well, there's no number in the real number system that does that, right? Because if you square a number and it's negative, you get a positive. If you square 0, you get 0. And if you square a positive, you keep the positive. So this is never going to happen in the real number system. So this is not real. Similarly, the fourth root of negative 625, this is not real. Now, I don't want you to get confused by what we looked at earlier. You can have a negative outside of the radical. So if I have the negative fourth root of 625, which we looked at earlier, this is just what negative number raised to the fourth power gives me 625. We know from earlier this is negative 5. These two are not the same. Notice how in this guy I have the negative inside. It's part of the radicand. Here my radicand is positive, so I'm good to go. My negative is on the outside. So make sure you understand the difference between the two because this is a common source of confusion. Now you might get in a scenario where you see an odd root of a negative number. This is allowed, right? We talked about these earlier in the lesson. We looked at some examples. Something like the cube root of negative 8, this is just negative 2. So this is a real number because negative 2 cubed is negative 2 times negative 2, which is 4, times negative 2 again, which gives you negative 8. You can raise a number to an odd power and get a negative. It's okay. Then something like the fifth root of negative 3,125, this is just negative 5. Because negative 5 raised to the fifth power would give me negative 3,125. All right, so let's talk a little bit about what happens when you work with variables. It's very important to understand that we can't take the square root or the fourth root or again an even root of a negative number. So when you work with variables, you don't know what the variable represents. So you have to be cautious. So if I have the nth root of x, I have to say that, okay, I can't plug in a negative value if n is even, right? So if n is even, then I have to assume that x is greater than or equal to 0. Otherwise, I'm allowing for the possibility of a non-real solution, okay? So you have to be very careful, and you might not have something that's just x. You might have an expression there, which we'll see in a moment. So if n is odd, then x can be any real number. X is any real number. Okay, it doesn't matter because, again, an odd number of negative factors is a negative, so that's okay. So if I have the square root of negative 81, this is, again, not real. Not real. The fifth root of negative 32 is just negative 2. Then something like the fourth root of negative 2,401, this is a 4. This is a negative here. Can't take the even root of a negative number. This is not real. Okay, not real. And again, in a few lessons, we'll learn how to deal with taking the square root of a negative. But for right now, we're just going to say it's not real. All right, let's talk about one more thing here. And this is very important also. So if I have the nth root of a to the n power, it's equal to the absolute value of a when n is even. And if I have the nth root of a to the n power, it's equal to a when n is odd. So this might seem like a peculiar rule, but I'm going to show you why it works in just a moment. So if I had something like the square root of x squared, we've been shown already that we can basically cancel what? The index here with the exponent. So most of you will cancel this with this and just say this is equal to x. Well, that's only true if x represents a non-negative real number. If that's the case, then you're fine. Suppose we had something like, let's say, the square root of 7 squared. Well, if this is a 2 here, this is perfectly valid. You can cancel this with this, and it's just 7, right? 7 squared would give me 49. Square root of 49 would give me 7, so that's okay. But if I had the square root of negative 7 squared, now I've got a problem. If you try to cancel this with this and say this is negative 7, that is wrong. Okay, this is wrong. This is where you need your absolute value. So we would cancel this back and say this is equal to the absolute value of x. So in other words, in this case, it's the absolute value of 7, which is 7. Here it's the absolute value of negative 7, which is positive 7. Okay? Why? Negative 7 squared is positive 49. So if I had the square root of negative 7 squared, this becomes the square root of positive 49, which is 7. Okay, not negative 7. So you're basically doing the squaring operation first before you take the square root. So it takes your negative into a positive, and then it's basically going to give you the absolute value of what was being squared. Okay, so that's how we have this rule. It's very important to understand when you're working with variables what restrictions are there. If your textbook tells you, hey, I want you to assume that all the variables are non-negative real numbers, then go ahead and cancel away, right? In this case, if we have that assumption, you can cancel this with this and say this is x. If you don't have that assumption, then you better make sure you put the absolute value of x, because on a test, the teacher will be looking for that and they'll mark it wrong. So something like the cube root of negative 11 cubed. Well, here I've got an odd index, so I can just cancel, right? It's not an issue, because if I cube a negative, I get a negative, right? So if I take the cube root of that, I would still have a negative. So here I can just cancel this with this, and this is just negative 11, right? So this is no problem, no issue. This is okay as long as you have an odd index. With this guy, I have an even index. So the fourth root of negative 6 to the fourth power, again, I can't just go through here and cancel. What I got to do is think about the fact that this would be equal to the absolute value of negative 6, which would just be 6, okay? And the reason for that is if I take negative 6 to the fourth power, I get 1,296, positive 1,296. If I take the fourth root of that, I go back to 6, right? So I just want the absolute value of this guy that's being raised to that power. That's going to end up giving me the correct answer, right? So please don't just cancel when you have an even index. Let's look at something a little bit more complex, but following kind of the same thought process. So the first thing I want to show you is that throughout the course, you will often see something like the square root of x minus 5. So for this guy right here, we need to figure out where it's defined, right? If we don't want to take the square root of a negative, then we've got to take our radicand here, which is an expression, and we've got to say, okay, this has got to be greater than or equal to 0. I would just solve this inequality. So I would add 5 to each side, and I would have x is greater than or equal to 5. So we would kind of put this restriction and say x is greater than or equal to 5 here. Because if it's less than 5, let's say it was 4. So you would have the square root of 4 minus 5, which is negative 1. And the square root of negative 1 is not real. Okay, not a real number. All right, so down here, we have something that's kind of similar to what we were looking at a minute ago. If we have the square root of the quantity x plus a squared, so some expression being squared here, we basically say that expression that's being squared, we're going to take the absolute value of that for the answer. So let me show you here. If we had something like the square root of x squared minus 10x plus 25, a lot of you know this is a perfect square trinomial. It can be factored into a binomial square. So this is the square root of x minus 5, that quantity squared. And essentially what I'm saying here is that you can't just cancel this with this. It's not equal to x minus 5. It's only going to be equal to that if x is greater than or equal to 5, okay? The case where the result under here is non-negative. And let me show you why it's equal to the absolute value of x minus 5. If x represented a value that gave me a positive here inside the parentheses, let's say x was 8 as an example. So I could plug in an 8 there. 8 minus 5 is 3. Absolute value of 3 is 3. So I know I would get 3 as an answer. So plugging in an 8 there, 8 minus 5 is 3. 3 squared is 9. The square root of 9 is 3. So I'm good to go. If I plugged in something that made it negative, though, think about this. If I plugged in, let's say, a 3. 3 minus 5 is negative 2. So I'd plug in a 3 here. Negative 2, the absolute value of that is positive 2. So this should be my answer. So plug in a 3 there. 3 minus 5 is negative 2. Negative 2 squared is 4. okay, positive 4. The square root of positive 4 is 2. If I didn't have that absolute value there, think about the fact that if I just went through and canceled, I would just be left with x minus 5. If I plugged in my 3 there, 3 minus 5 is negative 2. So I would have the incorrect answer of negative 2. Okay, so that's why you've got to have those absolute value bars there. It's to include scenarios where this guy ends up being negative, you square the negative, and you get a positive. Then when you take the square root, you've got to involve the absolute value operation. Okay, so very important you understand that. All right, so the square root of x squared minus 4x plus 4. Again, we have another perfect square trinomial. I would factor this and say this is the square root of x minus 2 squared. And I could say this is equal to the absolute value of x minus 2. Okay? Again, if we wanted to just define this for x being greater than or equal to 2, then we can cancel. So if I put a restriction here and said that x is greater than or equal to 2, well, then I can just go through and cancel. I can say the square root of x minus 2 squared. I can cancel this with this, and I can say this is x minus 2. That's perfectly legal because no matter what, x is greater than or equal to 2. So if I put a 2 there, I get 0. Square root of 0 is 0, so I'm okay. If I put a number larger than 2 there, I'm good to go. I can't put anything less than 2 because that would give me a negative here, and that would result in me having to use absolute value bars. So as long as you put this restriction in here, or the restriction is given to you, then you're good to go, okay? You don't have to go through and use absolute value bars. But if I take this away, then I've got to make sure that this is the absolute value of x minus 2 to account for the fact that this expression could be negative. We're squaring the negative, we get a positive, we take the square root. Again, you need the absolute value operation for that scenario. In this lesson, we want to review simplifying radicals. So one of the first steps to simplifying a radical is understanding the product rule for radicals. This rule allows us to multiply two radicals together with the same index. So if I had the nth root of a times the nth root of b, the index is the same. We'd have the nth root of a times b. So again, notice that this part, and this part are the same, right? It's got to be the same index. Then we just multiply the radicands together. So under the radical symbol, you have this radicand multiplied by this radicand. Okay, that's what we have there. So a couple of examples, if I had something like the square root of 2 times the square root of 3, this would be what? Got a square root and a square root, so it's the square root of 2 times 3, which is 6. Okay. If you had a higher level root, it's the same thing. If you had the cube root of, let's say, 7 times the cube root of, let's say, 5, this is the cube root, right? Index stays the same, of 7 times 5, which is 35. So very, very simple process, very easy to understand. What we're going to need to do is kind of reverse this to simplify. So in other words, if I see something like the square root of 40, I want to write this in such a way that I can simplify. So what do I mean by that? Well, let's take 40, for example, and let's factor it. So 40 factors into 8 times 5, and 5 is obviously prime. 8 factors into 4 times 2, and we know 2 is prime. 4 factors into 2 times 2, and again, we know 2 is prime. So what am I looking for? If I have a square root, I'm looking for factors of 40 that are a perfect square. In other words, I'm looking for factors of 40 where their square root is a rational number. So 4 is a perfect square because it's 2 times 2, right? So I can write this as the square root of 4 multiplied by 2 times 5 is 10, so the square root of 10, okay? Haven't done anything illegal. Notice that if you had been presented with the problem, the square root of 4 times the square root of 10, by the rule we just learned, we could write this as the square root of 40. Now, this wouldn't be considered simplified, but we could still do it. Now, let's erase this. I want you to think about what you can do here. The square root of 4 we just said was 2. So what I want to do to make this more simple is just replace that with a 2. So I'm going to put 2 times the square root of 10. So the square root of 40 and 2 times the square root of 10 represent the same value. It's just that this guy right here, 2 times the square root of 10, is considered simplified. All right, let's take a look at another example. So suppose you had the square root of 54 and you wanted to simplify. Again, just go ahead and factor 54. So we know this is 9 times 6. And you can pretty much stop there. You know 9 is 3 times 3, right? So 9 is a perfect square. 6 is going to be 3 times 2, but nothing you can really do with that. So I could write this as the square root of 9 multiplied by the square root of 6. Let me erase this, get this out of the way. And we know the square root of 9 is 3, so we're just going to write that. So this is 3 times the square root of 6. Again, square root of 54 and 3 times the square root of 6 represent the same number. It's just that this guy right here, 3 times the square root of 6, is considered simplified. All right, we can also do this process with higher roots. Suppose you had the cube root of 128. So the first thing I'd want to do again is just factor the number. And 128, a lot of you do know that that is 2 to the 7th power. But if you didn't, you could start by saying, okay, it's 64 times 2. 64 is 16 times 4. 4 is 2 times 2. 16 is 4 times 4, and 4 is 2 times 2. And so you have 1, 2, 3, 4, 5, 6, 7 factors of 2. Now, if I want the cube root of something, I am looking for factors of this number right here, of this radicand, that are going to be a perfect cube, meaning the cube root of the number is a rational number. So if I look here, I can do 2 times 2, 2 times 2, and 2 times 2, right? So I would have 1, 2, 3 of those guys. In other words, I would have 4 to the 3rd power, which is 64, times 2. So I could write this as the cube root of 64, which we know is 4, times the cube root of 2. Okay, all I did was break this down. Just because it's a cube root doesn't mean the process is any harder or more difficult. It's the same thing. Instead of looking for a perfect square like you would with a square root, you're looking for a perfect cube because you have a cube root, okay? So all we're going to do is just replace this guy right here with a 4, okay? Cube root of 64 is 4, then times the cube root of 2, okay? So again, 4 times the cube root of 2 is the simplified version of the cube root of 128. All right, so for the next one, we have one with a variable involved. So we have the square root of 50x cubed. So the square root of 50 is very easy to simplify. We pretty much mastered that at this point. We should know that 50 is 25 times 2, and 25 is a perfect square. So I could write this as the square root of 25 times the square root of 2. Pretty simple. We know that this guy right here, the square root of 25 is just 5. All right, but we need to deal with this part right here. So off to the side, if I had the square root of x cubed, what does that simplify into? Well, there's a lot of different ways to think about this. First and foremost, can you simplify? The rule is if this exponent here is larger or equal to this index here, yes, you can simplify. So if I have x cubed here, and my index here is a 2, right? I'm taking the square root of that. I want to think about the next exponent going down that's going to be divisible by 2, my index. Why? Well, if I rewrote this as the square root of x squared times the square root of x, this guy right here would simplify to x, okay? How do I know that? Well, again, if I wrote this using exponential notation, this is x squared raised to the power of 1/2. So this is what? It's x raised to the power of 2 over 2, which is 1, okay? That's the simplest way to kind of think about it. Another way to think about it is to visibly write an index here and just say this guy right here, the 2, the exponent there, is going to be divided by this guy right here, the index. 2 divided by 2 is 1, so you would just have one of those guys. So to simplify this, I would break this up and say this is the square root of x squared times the square root of just x, okay? And again, we already know that this part right here can just be written as x. So we're just going to say that this square root of 25 is 5, square root of x squared is x, and then times what's left over. The square root of 2 times the square root of x is written as the square root of 2x. So we end up with 5x times the square root of 2x. All right, let's take a look at another one with a variable in it. So we have the 4th root of 80x to the 9th power. All right, so I'm looking for a number here that is a factor of 80, and that's a perfect 4th, okay? So if I was to factor 80, what would I get? Well, it just so happens I would get 16 times 5, And 16 is 2 to the 4th power. We don't need to go through the whole factorization. So I'm going to write this as the 4th root of 16 times the 4th root of 5. Okay? This part right here would simplify to 2. Right? 2 to the 4th power is 16. So the 4th root of 16 is 2. Right? 16 is a perfect 4th. Then for x to the 9th power, again, we got to think about this. So x to the 9th power, if I have the 4th root of that, first question, can I simplify? The 9 is larger than the 4, so the answer is yes. Now, if I want to do this, think about the next exponent going down, that's divisible by 4. If I think about 9, 9 is not divisible by 4, but 1 down, 8 would be. So I'm going to rewrite this as the 4th root of x to the 8th power times the 4th root of x, right? X to the 8th times x is x to the 9th, so this is completely legal. Now, I can either use exponents, or again, I can just divide this by this. 8 divided by 4 is 2, so this would end up being x squared. Okay? So put times the 4th root of x to the 8th power times the 4th root of just x. And again, this guy is going to simplify to x squared. And again, if you want to see that using exponential notation, that's one of the ones that really helps students if they're struggling. If you have the 4th root of x to the 8th power, this x to the 8th power would be here. It's raised to the 1/4 power. Just think about the fact that this guy right here is always going to divide this guy right here. So it's the 8 here, the exponent, divided by the index here. That's why I do that so quickly. When I use my power to power rule, this becomes x raised to the power of 8/4, which is x squared. All right, so now let's go ahead and write this. We know the 4th root of 16 is 2, so we'll put 2. We know the 4th root of x to the 8th power is x squared, so we'll put that. And then times the 4th root of, what do we have left? We have a 5, and then times an x. So times the 4th root of 5x. So our answer here is 2x squared times the 4th root of 5x. All right, so for the next part, let's talk about the quotient rule for radicals. So if we had the nth root of a over b, this is equal to the nth root of a over the nth root of b. So this would help us if we had something like, let's say, the square root of 4 over 9. Right now that looks kind of hard to solve. So you can break this up and say it's the square root of 4 over the square root of 9. So you're attacking the numerator and denominator kind of separately there. The square root of 4 is 2. The square root of 9 is 3. So we get 2/3 as our answer. Okay, pretty simple. So suppose you saw something like the square root of 7/64. So all I'm going to do is just break this up and say this is the square root of 7 over the square root of 64. The square root of 64 is 8. So I would write the square root of 7 over 8. I can't do anything else with the square root of 7. 7's a prime number. Nothing else I could do. So this is as simple as you can make this. Square root of 7 over 8. All right, let's look at another one with a variable involved. So we have the 4th root of 625x to the 5th power over y to the 12th power. Okay, so I'm just going to break this up. So I would have the 4th root of 625x to the 5th power over the 4th root of y to the 12th power. So the denominator is very easy, right? Again, if this guy is greater than or equal to this guy, then think about if they're divisible by each other. So 12 is divisible by 4. I don't need to do anything else. 12 divided by 4 is 3. So I can just write this as y cubed. I'm done. Okay, I don't have to do anything else. Up here, I've got the 4th root of 625 times the 4th root of x to the 5th power if I wanted to break it up. So the 4th root of 625 times the 4th root of x to the 5th power. Now, I know I can simplify here because the 5 is larger than the 4. We'll get to that in a second. The 4th root of 625 is 5, right? Because 5 to the 4th power is 625. So let's go ahead and just simplify this. We know that's a 5. So we would have a 5 multiplied by the 4th root of x to the 5th power over y cubed. Now, how do we simplify this? Again, if this guy, which is a 5, is greater than or equal to this index, which is a 4, we know we can simplify. Again, think about, is 5 divisible by 4? No. The next number down that would be a 4. So I'm just going to break this up and say this is 5 times the 4th root of x to the 4th power times the 4th root of just x over y cubed. Okay? So this guy right here, again, if I divide this by this, I get 1. So we would have 5 times just x, right? It'd be x to the first power. Then times the fourth root of x, and then over y cubed. All right, now let's talk about how we can multiply radicals with a different index, okay? This is something that's pretty tedious, but you need to know how to do it in case it comes up. So if we had something like the square root of 7 multiplied by the cube root of 3, what do? You can't just multiply the radicands together and, throw some index in there randomly. What you have to do is find the least common multiple between the indexes. So if this is a 2 and this is a 3, the least common multiple is 2 times 3 or 6. So I'm going to write this in exponential notation to make it really easy. So this is 7 to the 1/2 power times 3 to the 1/3 power. And all I'm going to do is write this with a common denominator, okay? The common denominator is going to be a 6 because that's going to be my common index. So multiply this by 3 over 3, multiply this by 2 over 2. You're going to get 7 raised to the power of 3 over 6 times 3 raised to the power of 2 over 6. And you can write this in exponent form like it is now, or you can go back to radical form, whatever you want to do. So we can essentially say this is 7 cubed, and we're going to take the 6th root of that, times, we're going to say this is 3 squared, and we're going to take the 6th root of that, okay? And you can even combine them under one radical, doesn't matter, however you want to do it. For most of these, you're going to end up using a calculator anyway. You just need to know how to do it. So what is 7 cubed? That's 343. What is 3 squared? That's 9. So you would have the 6th root of 343 times 9, which is the 6th root of 3087. 3087. All right, let's talk about one last concept before we wrap up the lesson. So we have something known as the power rule for radicals, and you can see this in radical notation or exponential notation. So if you have a raised to the power of 1 over n, and then you raise this to the power of 1 over m, a stays the same. You're using your power to power rule. Basically, you multiply the exponents, you get a raised to the power of 1 over m times n. In radical notation, if you have the mth root of the nth root of a, basically this radicand here of a is going to stay, right? So when you write your radical here, the radicand is still a. You get your index as the product of these two indexes, so m times n. So suppose we had the 4th root of the cube root of 5. So based on what we just saw, we know we would have a radicand of 5. And we know we would just multiply these indexes together. So 4 times 3 would be 12. This is the 12th root of 5. But again, if you're struggling, you could start out by writing this inside guy right here as 5 to the power of 1/3. And then this guy is being raised to the power of 1/4, right? So this guy, 5 stays the same. Power to power rule, 1/3 times 1/4 is 1/12. 5 to the 1/12 power is the same thing as the 12th root of 5. All right, for the last problem, we're going to look at the 7th root of the square root of 14x. And again, all I'm going to do is I'm going to take this guy right here, this 14x. I'll write that as the radicand. And then for my index, this guy is a 2, this guy is a 7. 7 times 2 is 14. I'll have the 14th root of 14x. Again, if you're struggling, you can write this as 14x. This whole guy is going to be raised to the 1/2 power. And then that's going to be raised to the 1/7 power. So this would be equal to 14x would stay the same. And this would be raised to the power of 1/2 times 1/7, which is 1/14. This whole thing would be in parentheses. So you could really write this as 14 to the 1/14 power times x to the power of 1/14, which is essentially what we have here, right? If it's inside of parentheses like this, it looks like that. But this is the same thing. They're equivalent because I could write this as the 14th root of 14 times the 14th root, let me make that better. Again, the 14th root of x. But you wouldn't want to do that. So we would just leave our answer in this format here and say that this is the 14th root of 14x. In this lesson, we want to review operations with radicals. So before we jump in and start working on some problems, let's just take a minute to review the concept of like radicals. So before we do this, let's think briefly about like terms. So we know if we have something like 3x and 7x, these are like terms, right? If I add 3x plus 7x, all I need to do is add 3 and 7. That gives me 10. And the common variable of just x comes along for the ride, right? These can be added because they're like terms. if I had something like negative 5x squared y squared, and let's say 3x squared y squared, again, these are like terms. You have the same variable parts exactly. You have x squared and x squared, y squared and y squared. So if I added these guys, let's say I did negative 5x squared y squared plus 3x squared y squared. Again, all I do is negative 5 plus 3, just those numbers, those coefficients. That gives me negative 2. And then times the variable parts that are the same. So that kind of common variable part. So x squared, y squared. Okay, that just comes along for the ride. If we got, let me erase this, something where we didn't have like terms. Let's say it was 3x to the fourth power minus 2x squared. Well, I can't just subtract here. I can factor out an x squared, but that really doesn't do anything for me. So there's nothing I can really do to make that simpler, right? I can't subtract there because I don't have like terms. I have an x to the fourth power and an x squared, so I just kind of leave that alone. The same concept is going to apply when we work with radicals. We've got to have the exact same radicand, okay, that's the number under the radical symbol, and we've got to have the same index. So if I had something like 4 times the square root of, let's say, 11, and let's say I had 5 times the square root of 11, these are like radicals, okay? This guy right here is a square root. It's got an implied index of 2. This guy is a square root. It's got an implied index of 2. And the radicand is 11, and the radicand is 11. So same index, same radicand. Those are like radicals, okay? As another example, suppose we had something like 5xy multiplied by the cube root of 2x. And let's say we had negative 11xy multiplied by the cube root of 2x. So these guys are like radicals. You have the cube root and the cube root, right? So the index is the same, a 3 and a 3. And then the radicand is the same. It's a 2x and a 2x, okay? So that's what you're looking for when you have like radicals. To give you an example of something that's not like radicals, suppose you had, I don't know, let's say the cube root of 2x squared y, and then let's say you had the cube root of 2x squared. These are not like radicals because although the index is a 3 in each case, the radicand is not exactly the same. You have 2x squared y and then just 2x squared, okay? So again, the index has to be the same and the radicand has to be the same for you to have what's considered like radicals. So when we do have like radicals, we can add or subtract by basically using the distributive property. That's kind of the slow way if you want to kind of factor things out. The fast way is just to work with the numbers that are multiplying the radicals. So just like we saw when we combined like terms, if you had 3x plus 5x, what would you do? You would do 3 plus 5, that's 8, and then times the common variable x. Well, it's the same thing here. If I have 2 times the square root of 7 plus 5 times the square root of 7, I'm just going to do 2 plus 5, that's 7, times this common radical, which is the square root of 7. And I can show this officially using the distributive property. It's just a little bit slower. I could factor out the square root of 7 from each of these. Okay, so if I factor that out, I'd have the square root of 7 out in front of some parentheses. And then inside I would have 2 plus 5, right? I'd have a 2 left here and a 5 left there. And if I did this operation, 2 plus 5 is 7, so I would get 7 times the square root of 7. But again, you don't want to go through this each time you add or subtract radicals. You just want to work with the numbers that are multiplying the radicals. So again, 2 plus 5 is 7, and then times this common radical of the square root of 7. Okay, very, very simple. All right, suppose we had 4 times the cube root of 11 minus 13 times the cube root of 11. Again, you have like radicals. You have a cube root in each case, so the index is a 3. You have an 11 and an 11 as the radicand in each case. So those are like radicals. So all I need to do is work with the numbers that are multiplying the radicals. So I have a 4 minus a 13. 4 minus 13 is negative 9. So I'm just going to put negative 9 times the cube root of 11. Okay, it's just that simple. All right, let's take a look at another one. So suppose we had 3 times the fourth root of 11xy minus 7 times the fourth root of 11xy. So just because we have variables involved doesn't change anything. I have the same index. I have a 4 and a 4, and I have the same radicand. I have 11xy and 11xy. So everything has to match. In this case, it does. So I'm going to do 3 minus 7, which is negative 4, and then times, I'm going to have the fourth root of 11xy. All right, let's take a look at some harder examples now. So suppose you see negative 3 times the square root of 2 plus 2 times the square root of 162 plus 2 times the square root of 128. Now, at first, it looks like you can't simplify anything because you don't see like radicals, right? You see a square root, a square root, and a square root, but you have a 2, 162, and 128 as your radicands. So what you need to do here is simplify everything first and then determine if you have like radicals. This guy right here, this 2 times the square root of 162, you know 162 is 81 times 2, right? 81 is a perfect square, so I know this can be simplified. This is 2 times the square root of 81 times the square root of 2. The square root of 81 is 9, so I could say this is 2 times 9 or 18 times the square root of 2. So let's put equals. You have negative 3 times the square root of 2 plus this guy is going to be 18 times square root of 2. Now what about this 2 times square root of 128? So 2 times square root of 128. This guy right here would factor into 64 times 2. So I could write this as 2 times the square root of 64 times the square root of 2. We know that 64 is a perfect square. It's 8 times 8. So I could say this is 2 times 8 or 16 times the square root of 2. So I'll put plus 16 times the square root of 2. And now that we have everything in its simplest form, we can see that we do have like radicals. We have a square root, a square root, and a square root. We have a radicand of 2, a radicand of 2, and a radicand of 2. So all I'm going to do is just combine the numbers that are multiplying that common radical. So negative 3 plus 18 is going to be 15. 15 plus 16 is going to give me 31. So this is 31 multiplied by the square root of 2. All right, let's look at one that's a little bit more challenging. So we have x squared y cubed times the cube root of 128x to the 4th power y to the 5th power minus you have the cube root of negative 54x to the 10th power y to the 14th power. So this one's going to be tedious. I'll warn you in advance. It just takes a while to simplify. So I'm just going to look at each one separately, and then we'll kind of come back up. So if I had x squared y cubed times the cube root of 128 x to the 4th power y to the 5th power. Let's think about each part separately. So let me kind of scroll down and get some room. So 128, I know that's 2 to the 7th power. So let me write the cube root of 2 to the 7th power. Now, if this exponent here is a 7 and this index is a 3, then I want to think about what number going down from 7 is going to be divisible by 3. It will be 2 to the 6th power. So let me go ahead and break this up into the cube root of 2 to the 6th power times the cube root of 2. This guy right here, all I got to do is divide this by this. 6 divided by 3 is 2, so this would be 2 squared or 4. So I'm going to go ahead and write this. I'm going to keep this part the same. X squared y cubed. This guy is going to simplify to a 4, so I'm going to put that on the front. And then times the cube root of 2. Now I'm not done because I still need to work on those variables there. So if I had the cube root of x to the 4th power, what would this be? Again, I think about this exponent and this index. What number going down from 4 would be divisible by 3? 3 would be. So I can say this is the cube root of x cubed times the cube root of x. This guy would simplify to what? 3 divided by 3 is 1, so that would be x, okay? So if I multiply that by x squared, this would now become x cubed. And out here I would have times the cube root of x, which I can just write that underneath here, okay? So now let's deal with the cube root of y to the 5th power. Again, what number going down from 5 would be divisible by 3? 3 would be. So I could write this as the cube root of y cubed times the cube root of y squared. This guy right here would simplify to y, so y times y cubed would be y to the 4th power. And this guy right here, there's nothing really I can do with it, so I'm just going to write a y squared underneath here, and I'm basically done simplifying this guy. So let me erase all of this, and I'm ready to drag this up. So I'm just going to paste that in here. So this part right here is going to simplify to this. So now let me put minus, and let me deal with this down here. So I have the cube root of negative 54 x to the 10th power y to the 14th power. So let's think about that guy now. So thinking about negative 54, if I have the cube root of that, let's go ahead and separate this into the cube root of negative 1 times the cube root of what? If I think about 54, it's 27 times 2. 27 is a perfect cube. 27 is 3 times 3 times 3. So then times the cube root of 2. So this can be simplified. The cube root of negative 1 is negative 1. This can be simplified. The cube root of 27 is 3. And this can't be simplified. So I'm going to say this is equal to, you would have negative 3 times the cube root of 2. Now again, I've got to deal with these variables. So I've got this x to the 10th power. So the cube root of x to the 10th power, again, to deal with this, I want to think about what exponent going down is divisible by 3. 9 would be, right? So I could write this as the cube root of x to the 9th power times the cube root of x. So 9 divided by 3 is 3. So this guy would simplify into x cubed. So let me slide this negative 3 down. And I'll put my x cubed next to that. Let me kind of move this over a little bit. And what I'm left with is the cube root of x. So I'll just write an x under there. So we can erase this for now. And now lastly, I have the cube root of y to the 14th power. Again, what number here going down from 14 is going to be divisible by 3? It's going to be 12. So I can write the cube root of y to the 12th power times the cube root of y squared. Okay? So this guy right here is going to simplify to y to the 4th power. Again, 12 divided by 3 is 4. So that would be y to the 4th power. This guy right here, I can't do anything with it. So I would write y squared underneath here because I have the cube root of y squared. Okay, so we've simplified the other guy now. Let's erase this. And let's go ahead and drag this up. Okay, so we'll put that there. Now notice we have minus and negative. So we're going to go ahead and just write plus here. Okay, minus a negative is plus a positive. So now I do have like radicals. I have the cube root and the cube root. I have 2xy squared and 2xy squared. Another thing is you got to have like terms, right? Because these guys right here have variables involved, so they got to be like terms for you to add anyway. But you do have that as well, right? You have x cubed, y to the 4th, and y to the 4th. So all I need to do is add 4 plus 3, that's 7. And then times x cubed, y to the 4th. And then times this common radical, which is the cube root of 2xy squared. And that's my answer. All right, let's take a look at another one that's pretty tedious. So we have x multiplied by the 4th root of 256x to the 5th power y to the 6th. Plus y multiplied by the 4th root of 625x to the 9th y squared. So let's try to, again, just separate things and simplify and then come back up. So x multiplied by the 4th root of 256x to the 5th power y to the 6th power. So let me scroll down and get a little room going. If I think about 256, it is 2 to the 8th power, so it's a perfect fourth, right? The 4th root of 2 to the 8th power, 8 divided by 4 is 2, so this is 2 squared, right? So this guy would be 2 squared, or 4, times x times the 4th root of x to the 5th power y to the 6th power. Then if I think about the 4th root of x to the 5th power, again, this is pretty easy at this point. What number going down from 5 is going to be divisible by 4? 4 would be. So I write this as the 4th root of x to the 4th power times the 4th root of x. This guy is just x, right? 4 divided by 4 is 1. So if I had x multiplied by x, it would be x squared. So you can get rid of this guy. And you're just left with the 4th root of just x. So go ahead and erase this 5 here. And that'll be done there. So what about the 4th root of y to the 6th power? Again, if you think about this number and this number, going down from 6, a 4 would be divisible by 4. So I can say this is the 4th root of y to the 4th power times the 4th root of y squared. Okay? So this guy is going to just be y, because 4 divided by 4 is 1. So I'll put a y out here. So that's gone. And then I'm thinking about the 4th root of y squared. So I'll change this to a 2 here. Okay? So let's erase all this and this. And let's go ahead and drag this back up to the top. All right, for this guy right here, we have y times the fourth root of 625 x to the ninth power y squared. So let's put plus. We already know 625 is a perfect fourth. The fourth root of 625 is 5. So I can go ahead and write this as 5y. And then I'll put a little bit of space here. So let me erase this. And now I'm just thinking about what is the fourth root of x to the ninth power? What is the fourth root of y squared? So what is the fourth root of x to the ninth power? And what is the fourth root of y squared? Well, this guy can't really be simplified other than the fact that this part right here and this part right here, they share a common factor of 2, but we'll deal with that in the end. So for right now, I'm just going to put the fourth root of y squared like that. And I won't have to worry about this for now. I just want to simplify this. So I know that this 9 here is not divisible by 4, but an 8 would be. So I can split this up and say this is the fourth root of x to the 8th power times the fourth root of x. So this is what's going to go underneath here. And notice you do have like radicals now. So I can get rid of that. The fourth root of x to the 8th power is going to be x squared, right? 8 divided by 4 is 2. So this becomes x squared here. And to write this in the same order, I'll put x squared first and then y. The order doesn't matter, but I don't want that to trip you up. So look at what you have. You have 4x squared y and 5x squared y. So those are like terms. And then you have the fourth root of xy squared and the fourth root of xy squared. Those are like radicals. So all we need to do is just add 4 plus 5 is 9, and then times x squared y. And then this is times the fourth root of xy squared. Now, between this guy right here and this guy right here, you have a common factor of 2. So you can further break this down and say that you have 9x squared y times the fourth root of x times, if I think about y squared, and we have the fourth root of that, well, in exponent form, this is y squared raised to the 1/4 power. So this is y raised to the power of 2 over 4, or y raised to the 1/2 power. So then you can put times the square root, okay, the square root of y, okay? And if you wanted to make that a little bit clearer, we can put a multiplication sign there because I know it's kind of jumbled up. So let's write this as 9x squared y. I'll put times the square root of y, and I'll put times the fourth root of x. All right, let's take a look at some easier problems now. So a lot of times when you work with radicals, you do involve multiplication. And this guy right here is just going to be using my distributive property. So the square root of 5 multiplied by the quantity, the square root of 7 plus 2. So just distribute the square root of 5 to each term. The square root of 5 times the square root of 7 is just the square root of 35. Nothing to simplify there. The square root of 5 times 2 is just 2 times the square root of 5. Okay, pretty easy. All right, for this guy, we're going to use FOIL. We have basically two binomials here. We have 4 plus the square root of 3 multiplied by 2 minus the square root of 3. So first terms, 4 times 2 is 8. Outer terms, 4 times negative square root of 3 is going to be negative 4 times square root of 3. Inner terms, square root of 3 times 2 is 2 times square root of 3. Then for my last terms, I have the square root of 3 times the negative square root of 3. So that's just going to be minus 3. So what can I combine? 8 minus 3 is 5. And then negative 4 times square root of 3 plus 2 times square root of 3 is negative 2 times square root of 3. So you get 5 minus 2 times square root of 3 as your answer. All right, let's do one more here. And you'll probably notice that we can use our special products formula pattern here. We have the square root of 13 minus 11 times the square root of 13 plus 11. So this is basically the product of conjugates, right? You have the same term here and here. You have the same term here and here. And you have opposite signs, right? A plus and then a minus. So all I need to do, I know the two middle terms will drop out. I just need to square the first guy. So if I squared the square root of 13, this would give me 13, okay? So I would have 13, and then minus, if I square 11, I get 121. So what is 13 minus 121? That's going to be negative 108, okay? Negative 108. In this lesson, we want to review rationalizing the denominator. So in order to present a simplified radical as an answer, you have 4 criteria that you need to meet. So first and foremost, we say that the radicand, that's the number under the radical symbol, has no factor raised to a power greater than or equal to the index. Now, what does this mean in layman's terms? We already talked about this a few lessons ago. Essentially, if you had something like the square root of 20, the index here is a 2 on a square root, so you don't want any factors of this radicand, this number 20, to be a perfect square. So with 20, we know this would factor into 4 times 5, and 4 is a perfect square. So we could write this as the square root of 4 times the square root of 5. This guy would represent the rational number 2. So we would just write this as 2 times the square root of 5, and that would be considered simplified, okay? If you had a cube root, then you don't want any factor of the radicand to be a perfect cube. If you had a fourth root, you don't want any factor of the radicand to be a perfect fourth, so on and so forth. All right, the next item on the list, the radicand has no fractions. We learned about the quotient rule for radicals. That's how we can deal with that. If you had something like, let's say, the square root of 12 over 25, we could break this up into the square root of 12 over the square root of 25. We know the square root of 25 is 5, so let's just write that down there in the denominator. For the square root of 12, we can simplify because it's 4 times 3, right? That's 12. So we have the square root of 4 times the square root of 3. So this guy right here, again, square root of 4 is just 2, so I can end up writing this as 2 times square root of 3 over 5, okay? Then this guy right here is the subject of today's lesson. We have no denominator contains a radical. So if I had something like, let's say, 4 over the square root of 2, we don't want a radical in the denominator. That's considered not simplified. So the process we use to clear a denominator of any radicals is known as rationalizing the denominator. Okay, and we'll talk about that just in a second. Now, lastly, we see that exponents in the radicand and the index of the radical have no common factor. So what this means is if you had something like, let's say, 5 to the 6th power, and let's say you had the 9th root of that. Well, between the 9 and the 6 there, you have a common factor of 3. So you can quickly say, okay, if I divide 9 by 3, I get 3. And if I divide 6 by 3, I get 2. So this would be the cube root of 5 squared, or basically the cube root of 25. Now, if that doesn't make sense for you doing it that way, you can always convert this to exponential form. You can say I have 5 to the 6th power raised to the 1/9 power. And of course, you can use your power to power rule. So this is 5 raised to the power of 6 times 1/9, which is 6/9. And from there, you can just simplify the fraction. 6 and 9, again, each have a common factor of 3. Divide 6 by 3, you get 2. Divide 9 by 3, you get 3. So this ends up being 5 raised to the 2/3 power, which again is just the cube root of 5 squared, which is the cube root of 25, okay? It's just simpler to divide here than to go through all this with the exponential form. But if it's something you struggle with, something you can't mentally comprehend yet, then go ahead and take the time, convert it to exponential form, and then you'll be good to go. Let's talk a little bit about rationalizing the denominator now. It's a pretty easy concept overall. So if I had something like 5 over the square root of 2, realize that you have a radical in the denominator. And again, if you want to present a simplified radical, this is not allowed. So right now, this square root of 2 is an irrational number. Okay, it's an irrational number. So in decimal form, it does not terminate, it does not repeat. So to simplify this, all I really need to do is multiply the numerator and denominator by the square root of 2. And let's think about why that works for a second. The first thing is the square root of 2 over the square root of 2 represents the number 1, right? It's just a complicated form of 1. I can always multiply by 1, and I leave my number unchanged. So I'm not doing anything illegal. In the numerator, 5 times square root of 2 is just 5 times square root of 2. Nothing fancy there. In the denominator, what's going to happen is square root of 2 times square root of 2 is the square root of 2 squared, or the square root of 2 times 2, which is just going to be 2, right? It's the square root of 4, which is 2. So this is going to be equal to 5 times square root of 2 over 2. So now this 2 is a rational number. So I've changed my denominator from an irrational number to a rational number, henceforth the term rationalizing the denominator. So basically to do this, especially if you're just working with a square root, just make sure your square root is simplified first. And then once that's done, just multiply the numerator and denominator by that square root. So let's look at another example. So if I had something like 6 over the square root of 3x. This guy right here is already simplified. So I'm just going to multiply this by the square root of 3x over the square root of 3x. And what would I get? 6 times the square root of 3x is just 6 times the square root of 3x. Down here, the square root of 3x times the square root of 3x is just 3x. Now, I'm not done because I can simplify further. Between the numerator and denominator have a common factor of 3. So this divided by this would give me what? That's gone. This would be a 2. So we end up with 2 times the square root of 3x over x. And that's my final answer. I can't do anything else. But again, notice how I don't have an irrational number in the denominator. I just have an x. All right, for the next one, we're going to look at one with a higher level root. So we have 7 over the cube root of 2. And essentially what I want to end up with is something in the denominator that's the cube root of something that's a perfect cube. So if I think about 2 times 2 would be 4, 4 times 2 would be 8. So I want to end up with the cube root of 8 because 8's a perfect cube. So I'm going to multiply this by the cube root of 4 because 2 times 4 would give me 8. And I got to do the same thing to the numerator to make it legal. So I would have 7 times the cube root of 4 over, again in the denominator, the cube root of 2 times the cube root of 4 would be the cube root of 8, which is just 2, right? So I'd have 7 times the cube root of 4 over 2. All right, for the next one, we'll look at 15xy over the cube root of 25x squared y. So if I think about 25, it's 5 squared. I know x squared is just x squared, and I know y is y to the first power. I need a perfect cube under here. So what I'm going to need is 5 cubed, I'm going to need x cubed, and I'm going to need y cubed. So what am I missing to get to 5 cubed? I just need a 5. So I'm going to have the cube root of 5. And then what am I missing to get to x cubed? I need an x. What am I missing to get to y cubed? I need a y squared. Okay? So everything under there would basically be a perfect cube after it's multiplied. So if I go through here, and I'll deal with the numerator in a second. If I go through here and multiply, 25 times 5 is 125. X squared times x is x cubed. And y times y squared is y cubed. So if I take the cube root of this, again, this is a perfect cube, I'm going to end up with 5xy as my denominator. Okay? So once I've figured that out, the numerator part is pretty easy. I'm going to have 15xy multiplied by the cube root of 5xy squared. So I'm just going to write this here. We have 15xy times the cube root of 5xy squared. And again, one more time down here. So 15xy times the cube root of 5xy squared. And we can do some simplifying here. We see between numerator and denominator, we have a common factor of 5, so this becomes 3. We have a common factor of x, so that's gone. And then we have a common factor of y. So this guy will cancel with this guy. And I'm basically just left with a 3 multiplied by the cube root of 5xy squared. Let me make that a little better. All right, let's take a look at another one. So we have 2x minus 5y over the fourth root of 125xy cubed z squared. Again, if I have a fourth root here, I'm looking to make this into a perfect fourth down here. So for 125, I know that's 5 cubed. For x, I know that's x to the first power. We have y cubed, and we have z squared. So what do I need to do to make this into a perfect fourth? 5 cubed, I'm missing a 5. X to the first power, I'm missing an x cubed. Y cubed, I'm missing a y. And z squared, I'm missing a z squared. So I need to multiply the numerator and denominator by the fourth root of 5x cubed yz squared. Okay, let me erase this. So this is equal to, I've got to be careful here because when I multiply this by this is 2 terms here, okay? So I've got to make sure that each term is multiplied by this. So I'm going to use some parentheses. I'm going to put my fourth root of 5x cubed yz squared out in front. And inside of parentheses, I'll have 2x minus 5y. Again, with two terms there, this has to be multiplied by each term. Then this is over. If I multiply these guys, I'll have the fourth root of 125 times 5 is 625. X times x cubed is x to the fourth power. Y cubed times y is going to be y to the fourth power. And z squared times z squared is z to the fourth power. So notice how we have a perfect fourth down here. So let's go through and keep simplifying. And I'll scroll down and get a little room going. So I'll have my fourth root of 5x cubed yz squared multiplied by the quantity 2x minus 5y. Then this is over. This guy right here, the fourth root of 625 is 5. Then the fourth root of x to the fourth power is x. The fourth root of y to the fourth power is y. And the fourth root of z to the fourth power is z. Now I can go through and I can distribute this to each term if you want, but it's not really necessary because this is as simple as we can really make it. But for the sake of completeness, we will clear these parentheses. So we'll say we have 2x times the fourth root of 5x cubed yz squared. Then minus, you're going to have 5y times the fourth root of 5x cubed yz squared. Then this is all going to be over. You're going to have that 5xyz. All right, let's talk a little bit about rationalizing a binomial denominator. So for this guy right here, it's a pretty easy concept. You're going to use your formula for multiplying conjugates to clear a binomial denominator that has a radical in it. So what do I mean by that? I want you to recall that if you have x plus y multiplied by x minus y, remember these guys are called conjugates. It's the same first terms, it's the same last terms, you have different signs, so a plus and a minus. When you multiply these two together, the middle two terms drop out. So you end up with just the first term squared minus the last term squared. So what's going to happen is I'm going to multiply this by, we'll have the square root of x minus 3 over the square root of x minus 3. Okay? So what I did was, in my denominator, I now have the product of conjugates. It's the same two terms, so square root of x and square root of x, 3 and 3, but different signs. So what's going to happen is the middle two terms are going to drop out. They'll cancel, and you'll be left with the first term squared, square root of x squared is x, minus the last term squared, 3 squared is 9. Okay? So if you want to go through that the long way, square root of x times square root of x is x. The outer would be minus 3 times square root of x. The inner would be plus 3 times square root of x. So you can see those would cancel. And the last would be minus 9. Okay, so this is gone, and you're just left with x minus 9, right, which is exactly what you have there. Then in the numerator, we basically have 1 times this quantity, which is just that quantity. So you get the square root of x minus 3 up there. Okay, nothing you can really do here to simplify further. So we just have the square root of x minus 3 over x minus 9. All right, let's take a look at another one. So we have the square root of x over 3 minus the square root of x. Again, I'm just going to multiply the numerator and denominator by the conjugate of the denominator. So I would have 3 plus the square root of x over 3 plus the square root of x. Again, it's the same two terms in the same order, just change the signs. Okay, that's all you've got to do. So in the denominator, I would just square the first guy. 3 squared is 9. Then minus square the last guy. Square root of x squared is just x. And then in the numerator, we would basically have 3 times square root of x. And then plus square root of x times square root of x would be x. Nothing else I can really do to simplify here. So 3 times square root of x plus x over 9 minus x is your answer. All right, for the last one, we'll look at one that's a little bit challenging. So we have 3x over, we have 2 plus the square root of x plus y. So the idea is to treat this as the first guy and this as the second guy. So if I want to multiply by conjugates here, I'm just going to say this is 2 minus the square root of x plus y. And then down here, I'm going to put 2 minus the square root of x plus y. Okay? So when you go through and multiply, it's the same principle. You'd square the first guy, which is 2. So that's 2 squared, which is 4. And then minus, you'd square this guy right here. So if I squared the square root of x plus y, I would just get x plus y. But you got to be careful because you got to subtract the whole thing away. Okay, so this would be minus x and then minus y. In the numerator, you would have 3x times 2, which is 6x. And then minus, you would have 3x times the square root of x plus y. Now, nothing you can do to simplify this further. You just get 6x minus 3x times the square root of x plus y over 4 minus x minus y. In this lesson, we're going to review solving radical equations. So when we talk about solving radical equations, this is an equation with a radical involved somewhere. So you might have a square root somewhere, a cube root, a fourth root, a fifth root, so on and so forth. So the way we undo a square root is by kind of squaring both sides. The way we'd undo a cube root is by cubing both sides. You know, a fourth root, we'd raise both sides to the fourth power, so on and so forth. But there's a kind of problem that comes up when we work with radical equations. To see what I'm talking about here, let's look at a simple example. Suppose you had something like x equals a number. In this case, we're just going to let that number be 10. If I squared both sides, so that would give me x squared is equal to 100. Notice how this new equation has more solutions than the original. So what do I mean by that? Well, we know from the last section where we talked about solving quadratic equations that x squared equals 100 can be solved by the square root property. This would be x is equal to plus or minus the square root of 100, which is 10. So this basically is x is equal to 10 or x is equal to negative 10. Okay, well, 10 works as a solution to the original equation. If I plug in a 10 for x there, I get 10 is equal to 10, which is true. That works. But if I use negative 10, let's say I plugged in a negative 10 there, negative 10 does not equal 10. This is false. Okay, this is false. So what happens here is that when we squared both sides, we lost a little bit of information. Okay, we don't know whether it was 10 that was squared or negative 10 that was squared, because 10 squared is 100, but also negative 10 squared is 100. So we don't know which was squared. So this guy right here, this x equals negative 10, is an extraneous solution. Okay, that's what we call a solution to a new equation, okay, that was formed that doesn't work in the original. Okay, so that guy is extraneous. So to guard against this, what happens is we have to check all of our proposed solutions when we're working with radical equations. All right, so for solving radical equations, the first thing you want to do is isolate the radical on one side of the equation. Then you're going to apply the power rule. So that just means if it's a square root you isolated, you raise both sides to the second power. If it's a cube root, you raise both sides to the third power, so on and so forth. So the next step is if a radical remains, you're going to repeat steps 1 and 2. So you're going to have to isolate again, and then again, if it's a square root, square both sides. If it's a cube root, cube both sides, so on and so forth. So once we've kind of dealt with all the radicals, we're going to solve the equation. Then we're going to check all potential solutions. So this guy is very important because, again, we want to guard against extraneous solutions. All right, let's take a look at the first example. So we have the square root of 10x plus 1 is equal to 9. All right, so in this particular case, my square root operation is already isolated on one side, and I just have a number on the other. So essentially, I just want to square both sides so I can clear that square root operation. Okay, so we have square root of 10x plus 1 is equal to 9. I'm just going to square both sides. We know that this index of 2 here cancels with this exponent of 2. So we know that the square root operation is basically gone, and I just have my radicand, which is 10x plus 1, and this equals, I've got to square this side as well, so this is 81, okay? So another way to think about this before I go further, remember you can always write this in exponential notation. So if you're struggling, you can say this is 10x plus 1 raised to the 1/2 power, and this is equal to 9. Okay, I haven't done anything illegal. I just wrote the square root of 10x plus 1 as 10x plus 1, that quantity raised to the 1/2 power. So now if I use the power to power rule here, it becomes very clear. 1/2 times 2 is basically 1. So this guy right here becomes an exponent of 1. So that's how I know I'm getting my 10x plus 1. Okay, so if it's not clear for you, By doing it in that way, you can always use exponents to make it a little bit cleaner. All right, let's scooch this up. And let's just solve this equation. So let's subtract 1 away from each side. This gives me that 10x is equal to 80. I want to divide both sides by 10 so that I can isolate my variable x. And so we know that this would cancel with this, and I get x is equal to 80 over 10 is 8. Okay, so this is my proposed solution here. X is equal to 8. We need to check, again, to guard against errors. So if I plugged in an 8 there, I would get 10 times 8, which is 80, plus 1, which is 81. So we would have the principal square root of 81 is equal to 9. That's 9 equals 9. So this guy does check out. So x equals 8 is the correct solution. All right, let's take a look at another one. So suppose we saw x is equal to 2 plus the square root of x minus 2. So again, the first thing I want to do is isolate the radical on one side of the equation. So that square root of x minus 2, I've got to isolate that. How can I do that? Well, I've got this 2 that's being added to it. So I'm just going to subtract 2 away from each side of the equation. We know this would cancel. On the left side, I would have my x minus 2. This is equal to, I'm going to have my square root of x minus 2. Okay, so now that I've isolated the radical on the right-hand side, I can square both sides to clear the radical, okay? But I've got to be careful here on the left. This is the quantity x minus 2 squared, okay? We haven't talked about this in a while, but again, a common error is for students to just say this is x squared minus 2 squared. That is wrong. Please don't do that. Remember, this is a quantity x minus 2 squared, so I have to go x minus 2, that quantity, times x minus 2, right? But again, we all know at this point we can use our special products formula. So I would square the first guy, which is x, so that's x squared, then minus 2 times this guy, which is x, times this guy, which is 2. So that would be minus 4x. And then plus this guy, 2, being squared, which is 4. Then this is equal to, if I squared the square root of x minus 2, I would just get that x minus 2. Okay, let's scroll down and get some room going. We'll come back up. So now I want to solve this guy. So let's go ahead and clean it up. Let's subtract x away from each side of the equation, and that's going to cancel. Let's add 2 to both sides of the equation, and that's going to cancel. So on the right, I know I'm going to have 0, right? On the left, I'm going to have that x squared minus 5x, right? Negative 4x minus x is negative 5x. And then plus 4 plus 2 is 6. Okay, so this is equal to 0. Now I can solve this with the quadratic formula. I can solve it with factoring, whatever you want to do. Factoring is a little bit easier here. So let's go ahead and set this up as x and x. This equals 0 over here. So what are my 2 missing kind of items here? I need 1 there and 1 there. Well, you need 2 integers whose sum is negative 5 and whose product is positive 6. So that would be negative 2 and negative 3, all right? So now I can use my zero product property, and I can set each factor equal to 0. So I'm going to set x minus 2 equal to 0. Then, or I'm going to set x minus 3 equal to 0. And to solve this guy on the left, I would just add 2 to both sides of the equation, and we get x is equal to 2. To solve this guy on the right, I would add 3 to both sides of the equation, and we get x is equal to 3. So these are our 2 proposed solutions. So let's copy this, and we're going to check. All right, so if I plugged in a 2 for x here and here, what would I get? I would get that 2 is equal to 2 plus the square root of 2 minus 2 is 0. So basically, this is just 2 equals 2. So this guy is going to check out. If I plugged in a 3 for x, so there and there, you would get that 3 is equal to, you have your 2 plus the square root of 3 minus 2 is 1. Square root of 1 is 1. 2 plus 1 is 3. So 3 equals 3. That does check itself out. All right, let's look at a harder example. So suppose we have the square root of 2x minus 2 minus the square root of 8x plus 1, and this is equal to negative 3. All right, so the idea here is that I've got 2 square roots. I've got to isolate one of them first, square both sides. Then I'm still going to have a radical, so I'm going to have to do it again. So this is just a more tedious problem. All right, so let's go ahead and add the square root of 8x plus 1 to both sides. And what I'm going to have here is that the square root of 2x minus 2 is going to be equal to, you'll have the square root of 8x plus 1 and then minus 3. Okay? So now I'm going to square both sides. This guy right here, I'm just going to have my 2x minus 2. This is equal to, again, you've got to remember, when you square this guy here, it's got to be expanded. Okay, so you could use FOIL or your special products formula. It doesn't matter, but you can't just distribute the exponent to each term there. Okay, don't do that. So if I squared the square root of 8x plus 1, I would get 8x plus 1. So that would be the first guy there. Then you have a minus here, so this would be minus. You're going to have 2 times this square root of 8x plus 1, and then times the 3. So 2 times 3 is 6, so let's just put a 6 there. Then plus the last guy here, 3 squared. Okay, let's scroll down and get some room going. All right, a lot to clean up here. So I know that 1 plus 9 is 10. So let me just write this as 10. And let me go ahead and subtract 10 away from each side of the equation now. So that's going to cancel. And let me subtract 8x away from each side of the equation. So that's going to cancel. On the left side, 2x minus 8x is going to be negative 6x. Then negative 2 minus 10 is minus 12. And this is equal to, you've got your negative 6 times the square root of 8x plus 1. Now, you have a number, which is negative 6, that is multiplying your radical. At this point, you can square both sides as it is, but to make it simpler, we're going to divide both sides by negative 6. Okay? All right. So we know that if we divide like this, we can split this up and say this is negative 6x over negative 6. And I could say plus negative 12 over negative 6, just to make that a little simpler. So on the left-hand side, I would have x and then plus 2, right? Negative 12 over negative 6 is 2. And this is equal to, this cancels, so I just have my square root of 8x plus 1. So now to clear this radical, I'm just going to square both sides of the equation. So I'm going to square this side, and I'm going to square this side. So the quantity x plus 2 squared, again, I've got to use my special products formula or use FOIL or whatever you want to do. Just don't distribute the exponent to each term. Okay, that's wrong. So this would be x squared plus 2 times x times 2, so 4x, and then plus 2 squared, which is 4. This is equal to, if I square this guy, I would get 8x plus 1. Okay, so now let's clean this up. Let's subtract 1 away from each side of the equation. That's going to cancel. Let's subtract 8x away from each side of the equation. And that's going to cancel. So I'm going to have that x squared minus 4x plus 3 is equal to 0. So again, I can solve this guy with factoring, or I can solve it with the quadratic formula, whatever you want to use. Probably easier to solve it just with factoring. So let's go ahead and put this as x here and x here. And 2 items that I'm missing here, those numbers would sum to negative 4 and give me a product of positive 3. So that would be negative 3 and negative 1. Okay? So now I can use my zero product property to get a solution. We'd have that x minus 3 is equal to 0, or x minus 1 is equal to 0. So if I solve this guy here, I add 3 to both sides of the equation. I get x is equal to 3. If I solve this guy right here, I add 1 to both sides of the equation. I get that x is equal to 1. So x equals 3 or x equals 1. So we're not done. We need to check these. So let's check x equals 3 first. So I'm going to plug in a 3 there and there. So 2 times 3 is 6. 6 minus 2 is 4. Square root of 4 is 2. Then minus. 8 times 3 is 24. 24 plus 1 is 25. So the square root of 25 is 5. So is 2 minus 5 equal to negative 3? Yes, it is. So that checks out. If I plugged in a 1 for each occurrence of x, what would I get? 2 times 1 is 2. 2 minus 2 is 0. So that's gone. 8 times 1 is 8. 8 plus 1 is 9. So you would have the negative square root of 9. Square root of 9 is 3. If I put a negative out in front, it's negative 3. So negative 3 equals negative 3. So x equals 1 checks out as well. All right, now let's look at 1 with an extraneous solution. Okay, so this guy right here, you're going to have a problem. So we have the square root of 7x plus 2 is equal to negative 3 minus the square root of 3 minus x. Okay, So on the left-hand side, this square root operation is already isolated. So let's get things started by just squaring both sides. So I have the square root of 7x plus 2. I'm going to square this side. And then I'm going to square this side. So negative 3 minus the square root of 3 minus x, again, squared. On the left, I'm just going to have my radicand, which is 7x plus 2. On the right, again, I've got to use my special products formula. So I'm going to go ahead and square this guy right here, this negative 3. So that's going to give me a positive 9. Then minus, you've got 2 times, you've got your negative 3, and then times the square root of 3 minus x. So negative 2 times negative 3 is 6. So let's put plus 6 there. And then times, again, that square root of 3 minus x. Now you have to be careful when you use this when the first term is negative, okay? We always account for this sign right here. If it's positive, then you get a positive there in the middle term. If it's negative, you get a negative there in the middle term, okay? But in this case, we have a negative as the first term, and you don't usually see that when you're working with these kind of sample problems, okay? So you have to account for this negative. So that's why we have a positive here, because we ended up with a negative times a negative. That gave us a positive, okay? So make sure you understand that. All right, then plus, we've got this last guy squared. If I squared the square root of 3 minus x, I would get 3 minus x. Okay, so let's clean this up now. We would have 9 plus 3, which is 12. Okay, so this is 12. If I subtract 12 away from each side of the equation, I would have 7x plus 2 minus 12 is negative 10. So you put plus negative 10 or minus 10, whatever you want to do. This is equal to, then I'm going to add x to both sides of the equation. And we know this is going to cancel over here. 7x plus x is going to be 8x. So let me erase this and just put 8x here. So then I have on the right-hand side just my 6 times the square root of 3 minus x. Now at this point I can square both sides, but it might be a little easier if I kind of divide both sides by 6. You're not going to get whole numbers, but I find it to be easier to work with smaller numbers, even if they're fractions, okay? So I'm going to divide both sides by 6. On the right side, I'm going to have the square root of 3 minus x. On the left side, you think about 8 over 6, that's 4/3, times x. And then I'm going to put plus. You have negative 10 over 6. Let's put minus 5/3, okay? Now, I'm going to square both sides. So I'm going to square both sides. So to use my formula, I'd square 4/3 x. So that would be 16/9 times x squared. Then this guy would really be a minus here, right? I wrote plus negative, but it's really a minus. So let's put a minus out in front. You have your 2 times the 4/3 x times the 5/3. Okay? So if I go through and multiply that, you have 2 times 4, which is 8, 8 times 5, which is 40. So this is 40 in the numerator, over 3 times 3, which is 9 in the denominator. Then plus, you're lastly going to have 5/3 squared. 5 squared is 25, and then 3 squared is 9. Okay, so this is equal to, over here, the square root of 3 minus x being squared is just 3 minus x. So now, what I want to do, to clean this up, I'm going to multiply both sides of the equation by 9. So if I multiplied these guys by 9, this guy right here, this guy right here, and this guy right here, the denominators would just be cleared, right? So you'd have 16x squared minus 40x plus 25. This equals, I've got to multiply each term here by 9. 3 times 9 is 27, then minus 9 times x is 9x. Okay, so let's clean this up. If I add 9x to both sides of the equation, that'll cancel. And then if I subtract 27 from both sides of the equation, that'll cancel. Okay, so on the left-hand side, I just have my 16x squared. And then negative 40x plus 9x would give me negative 31x. And then 25 minus 27 is minus 2. And this equals 0. Okay, so I'm going to solve this using my quadratic formula. And so basically, let me scroll down a little bit. I know that this 16 is my value for A. The negative 31 is my value for B, and the negative 2 is my value for C. So x is equal to the negative of b. b here is negative 31, so that's 31, plus or minus the square root of b squared. If I squared negative 31, I would get 961. Then minus, you've got 4 times a is 16, times c is negative 2. So negative 4 times 16 is going to be negative 64. Then times negative 2 is positive 128. So you'd basically have a plus 128 there. So 961 plus 128 is 1,089. So this is 1,089. Then this is over. You've got 2 times a is 16, so this is 2 times 16, which is 32. Now the square root of 1,089 is 33, okay? So this is 33 here. So this gives me two solutions. We've got that x is equal to 31 plus 33 is 64, and 64 over 32 is 2. The other solution is 31 minus 33, which is negative 2 over 32. So negative 2 over 32. Each is divisible by 2 there. This would be a 1, and this would be a 16. So let's go ahead and check these. Okay, so let's start out by checking x equals 2. So if I plugged in a 2 there and there, what would I get? Well, 7 times 2 is 14. 14 plus 2 is 16. The principal square root of 16 is 4. This equals, over here, we'd have a 2 for x, so 3 minus 2 is 1. Square root of 1 is 1. So you'd have negative 3 minus 1. Negative 3 minus 1 is negative 4. That does not work out. 4 does not equal negative 4. This is false. So go ahead and mark this one off. Okay, that's not a solution. That one is extraneous. Then let's try negative 1/16. Okay, so we're going to plug that in. So here and also here. So this one's going to be a bit messy. So 7 times negative 1/16 is negative 7/16. Then plus 2. I get a common denominator here by multiplying 2 by 16 over 16. So that would be 32 over 16. So negative 7 plus 32 is going to be 25. So what I'd have here is I'd have the square root of 25 over 16, which basically is 5/4. Okay, so that's my left side. On the right side here, if I have 3, let me kind of slide this over. If I have 3 minus, again, negative 1/16, so I can put plus 1/16. Well, what's going to happen is I need to get a common denominator, so I'll multiply this by 16 over 16. 3 times 16 is 48. So you'd have 48 plus 1, which is 49. So this is 49 over 16. So the square root of 49 over 16 is 7/4. Okay? So you'd have negative 3 minus 7/4. To get a common denominator here, let me multiply this by 4 over 4. So this would be negative 12/4. So I ended up with negative 12 minus 7, which is negative 19 over 4. So we can clearly see that this one doesn't work out either, okay? This is also an extraneous solution because 5/4 does not equal negative 19/4, right? This is false. Okay, let me make that a little bit better. So in this particular case, you do not have a solution for your equation. You can go ahead and just mark this as no solution. No solution. In this lesson, we want to continue to review solving radical equations. All right, let's go ahead and take a look at an example with some cube roots involved. So we have the cube root of 4x plus 3 is equal to the cube root of 2x minus 1. Again, the idea here is the same. You want the radical isolated on one side of the equation. In this case, we have a radical on one side and a radical on the other. So they're both isolated. So all I need to do is use my power property. And that just tells me I can raise both sides of the equation to the third power since I have a cube root in each case. So let me just rewrite this. I have the third root of 4x plus 3. I'm going to raise this to the third power. This is equal to the third root of 2x minus 1. I'm going to raise this to the third power. Okay, so we know that the index here would cancel with the exponent here. I'm just left with the radicand. So 4x plus 3 is equal to, again, index with exponent, just left with the radicand, so you have your 2x minus 1. So from this point, it's really easy to solve. I would subtract 3 away from each side of the equation. And I will subtract 2x away from each side of the equation. And this is going to cancel, and this is going to cancel. 4x minus 2x is going to give me 2x, and this is equal to negative 1 minus 3 is going to be negative 4. Divide both sides of the equation by 2 so that we can isolate our variable x. This cancels with this. I get x is equal to negative 2. Okay, so again, we said x was equal to negative 2. Let's plug in a negative 2 there, and then also there. So we would have the cube root of 4 times negative 2 is negative 8. Negative 8 plus 3 is negative 5. So the cube root of negative 5 is equal to the cube root of 2 times negative 2 is negative 4. Negative 4 minus 1 is also negative 5. So you get the cube root of negative 5 is equal to the cube root of negative 5. It's the same value on both sides of the equation. So we can go ahead and check this off and say x equals negative 2 is the correct solution. All right, let's go ahead and look at another one. So we have 4 times the cube root of x minus 4 plus 36 is equal to 28. Again, the idea is to isolate the radical on one side of the equation. We can then use the power property to get rid of the radical. So what I'm going to do here is I'm going to subtract 36 away from each side of the equation, and this will cancel. So I'll have 4 times the cube root of, we've got our x minus 4 there, and this is equal to 28 minus 36 is going to give me negative 8. All right, so at this point, since I have 4 times the cube root of x minus 4, I can cube both sides of the equation. But again, it's always easier if you get rid of this part right here that's multiplying the radical. So I'm going to divide both sides by 4. Sometimes when you do this, the number on the other side of the radical is not going to be an integer or whole number if you want to think about it that way. You'll sometimes have to deal with a fraction. I prefer to do that, but you might not. Okay, and a lot of books will not do that if they get a fraction on the other side. So in this case, it turned out to be an integer. So this is going to cancel with this. We get the cube root of x minus 4 is equal to negative 8 over 4 is negative 2. Now we can cube both sides to get rid of that radical. So I know that this index here will cancel with this exponent. I'm just going to have my x minus 4, that radicand. This is equal to negative 2 cubed is negative 8. Okay? So very easy to solve this equation. I just add 4 to both sides of the equation, and I get x is equal to, let's go ahead and visibly cancel this. Negative 8 plus 4 is going to be negative 4. So that's my solution. Let's go ahead and check it. All right, so if I plugged in a negative 4 there for x, what would I get? So you would have 4 times the cube root of negative 4 minus 4, which is negative 8. And let me make that 3 a little bit better. Then plus 36 is equal to 28. Okay, so the cube root of negative 8 is negative 2. So I can say I'd have 4 times negative 2, which would be negative 8, plus 36 equals 28. And this is a true statement. Negative 8 plus 36 is 28. So you get that 28 is equal to 28. So I can go up here and say that x equals negative 4 is the correct solution. All right, let's take a look at one with a fourth root involved. So we have the fourth root of x squared minus 16 is equal to 2. So very easy to solve this. If I want to get rid of a radical with kind of an index of a 4, I'm just going to raise both sides of the equation to the 4th power, right? This guy's already isolated for me. So again, I've got the fourth root of x squared minus 16 is equal to 2. I'm going to raise this side to the 4th power and this side to the 4th power. So I know that, again, this index cancels with this exponent, and I just have my radicand. So I have x squared minus 16 is equal to 2 to the 4th power is 16. So let me scroll down and get some room going here. To solve this, I'm going to add 16 to both sides of the equation. That's going to cancel. I'll have x squared is equal to 32. I can solve this using my square root property. So I know this would be x is equal to plus or minus the square root of 32. Now, 32 is 16 times 2. 16 is a perfect square, right? The square root of 16 is 4. So let me kind of get some more room going here. I'll say this is x is equal to plus or minus, again, the square root of 16 is 4, then times the square root of 2, okay? So this is my solution. You can say that x is equal to 4 times square root of 2, or x is equal to negative 4 times square root of 2. All right, we have the fourth root of x squared. So if I squared 4 times the square root of 2, let's do that off to the side. So 4 times square root of 2. If I squared this, I would end up with what? Square 4 and you get 16. You square the square root of 2 and you get 2. So 16 times 2 would be 32. So this guy would be 32 minus 16. And this should equal 2 over here. So 32 minus 16 is 16. And the fourth root of 16 is 2. Okay? So this guy right here does check itself out. Now, you're going to get the same thing when you plug in this guy right here, because the negative there gets squared. Okay? So the negative 4 times the square root of 2, if you square that whole thing, you would again end up with 32. 32 minus 16 is 16. The fourth root of 16 is 2. So this guy would check itself out as well. All right, let's look at a more challenging problem. So we have the square root of 2 times the square root of 7x plus 2 is equal to the square root of 3x plus 2. So the easiest way to kind of solve this problem is to use exponents. So I'm going to rewrite this and say that I have 2 times the quantity 7x plus 2. So this guy right here, if you notice, is just underneath a square root symbol. So that means it's raised to the 1/2 power. So that part's raised to the 1/2 power. And then this whole thing here is raised to the 1/2 power. Okay, think about that. The 2 times the square root of 7x plus 2 is underneath this radical here. Okay, so the whole thing is raised to the 1/2 power. But you've got another 1/2 power that's going to surround the 7x plus 2. Okay, so make sure you understand how to set that up. So once we have this, we'll use our power to power rule, and we'll do that in a minute. This is equal to, this guy's easy, it's just 3x plus 2 inside of parentheses, again, raised to the 1/2 power. Okay, let's scroll down and get some room going. So now, because this is multiplication here, I can bring this exponent inside to kind of each guy that's involved in this multiplication. So 2 will be raised to the 1/2 power. And then we have times the 7x plus 2 raised to the 1/2 power is now raised to the 1/2 power again. So I'm going to use my power to power rule and say I have 7x plus 2 raised to the power of 1/2 times 1/2, which is 1/4. And this equals, you've got your 3x plus 2 raised to the 1/2 power. Okay, let's scroll down and get some room going. So how can we solve this equation? Well, we're going to look for the LCM of the denominators and basically raise each side to this power. In this case, it's a 4, okay? So I want to raise both sides to the 4th power. That's going to basically clear all those fractional exponents. So I'm going to raise this side to the 4th power, and I'm going to raise this side to the 4th power, okay? So again, power to power rule, I would have 2 raised to the power of 1/2, which is raised to the 4th power. So 4 times 1/2 is 2. So this is 2 squared times, you've got the quantity 7x plus 2 raised to the 1/4 power raised to the 4th power. So the 7x plus 2 part stays the same. 1/4 times 4 is 1. Okay, and this equals, over here I've got the quantity 3x plus 2 raised to the 1/2 power and then raised to the 4th power. Again, 3x plus 2, that quantity stays the same. Then I multiply 1/2 times 4, which is 2. Okay, let's scroll down and get some more room. All right, so we know that 2 squared is 4, and we basically have 4 times 7x, which is 28x, and then plus 4 times 2, which is 8. Then this is equal to, you would have this guy right here that you need to expand. Again, this is applying to something that has addition involved. This is not multiplication, so you can't distribute the 2 to each kind of term in there. You have to FOIL this out, or again, use the special products formula. So to use the special products formula, I would square 3x, which is 9x squared. Then plus, you have 2 times this term, 3x, times this term, which is 2. Then plus your final term, 2 squared, which is 4. Now 2 times 3 is 6. 6 times 2 is 12. So this would be 12x in the middle. Okay, so let's see what we got going here. We can go ahead and subtract 8 away from each side of the equation and subtract 28x away from each side of the equation. So this is going to cancel over here and here. And I'll just say this is a 0. So I'll have that 9x squared And then 12x minus 28x is negative 16x. So we'll put minus 16x. And then 4 minus 8 is negative 4. And this is equal to 0. So let's copy this and bring this to a new page. Okay, so we can use our quadratic formula on this. So x would be equal to the negative of b. B in this case is what? It's negative 16, right? Because this is a, this is your b, this is your c. So the negative of negative 16 is 16, plus or minus the square root of b squared. Negative 16 squared is 256. Then minus 4 times a is 9, times c is negative 4. So what's this going to give me? Negative 4 times 9 is negative 36. Then times negative 4 is 144. So 256 plus 144 is 400. If I have the square root of 400, that would be 20, okay? So write this as a 20 here. Then this is over 2 times a. Again, a is 9, so this is 18. So I've got two solutions here. I've got x is equal to 16 plus 20, which is 36, over 18, which is 2. And then x is equal to 16 minus 20, which is going to be negative 4 over your 18. Now this one can be reduced, right? If I divide both of these by 2, I would get negative 2 over 9. All right, so let's go ahead and check these solutions. So if I plugged in a 2 here and here, what would I get? Well, on the right side, 3 times 2 is 6. 6 plus 2 is 8. So this would be the square root of 8. We know that simplifies into, square root of 4 is 2, so this would be 2 times square root of 2. 2 times square root of 2. What do I have over here? 7 times 2 is 14. 14 plus 2 is 16. So the square root of 16 is 4. So I would have the square root of 2 times 4, which we know is 8, right? The 4 can come out there, and you would have 2 times square root of 2. So 2 times square root of 2 on each side of the equation. So we can check this one off. All right, let's look at one that's a little bit more tedious to check. So now we're going to look at the negative 2 ninths. So on the right side, 3 times negative 2 ninths. So 3 times negative 2 ninths. We can see that this cancels with this and gives me a 3 there. So you would have negative 2/3. You would have negative 2/3 plus 2. So get a common denominator going here. I'd multiply this by 3 over 3. 2 times 3 is 6. So you would have 6 plus negative 2, which is 4. So you'd basically have the square root of 4/3 here. So the square root of 4/3. If you split that up, you would get 2. You would get 2 over the square root of 3. Now, you can rationalize the denominator there, but it's not necessary because this isn't your answer, right? You don't need to present a simplified answer here. You're just checking to make sure you get 2 over square root of 3 on the left side, and you'll be good to go. All right, so let me kind of slide this out of the way. I'll put this over here for now. So on the left, 7 times negative 2 ninths is what? You would get negative 14 ninths. You would get negative 14 ninths. Then plus, get a common denominator here. If I'm adding 2, I can write that as 18 ninths. So essentially what I would have here is negative 14 plus 18, which is 4. So you get 4 ninths there. Okay, so 4 ninths. So the square root of 4 ninths, square root of 4 is 2, square root of 9 is 3. So you get 2/3. So you would have 2 times 2/3 underneath a square root symbol. We know that would be the square root of 4/3, which is exactly what we had over there. Square root of 4 is 2. Square root of 4 is 2 over the square root of 3. Again, I don't need to rationalize this because I'm just checking to make sure I get the same value on the left as I get on the right, and I did. So 2 is a valid solution, and so is negative 2 ninths. All right, let's take a look at one more of these. And what we're going to find here is that we have a mix of indexes, okay? So we have the square root of x plus 3 is equal to the cube root of 2x plus 5. So what do we do in this situation? I can't just raise both sides to the second power because that's not going to clear all the radicals. I can't just raise both sides to the third power because that's not going to clear all the radicals. So what you need is you need the LCM between the two indexes. You need to raise both sides to that power. That's how you're going to clear both radicals. So since this index is a 2 and this one's a 3, I need to raise both sides to the 6th power, okay? So I would say this is the square root of x plus 3. I'm going to raise this to the 6th power. And this over here is the cube root of 2x plus 5. I'm going to raise this to the 6th power. Now, if it's easier for you to kind of conceptualize this with exponents, that's fine. You could write this as x plus 3 to the 1/2 power. And then raise that to the 6th power. And you can write this as 2x plus 5 to the 1/3 power. And then raise that to the 6th power. Perfectly fine. Okay, it doesn't matter which way you do it. Now, the power to power rule, if I have x plus 3 raised to the 1/2 power and then it's raised to the 6th power, then my x plus 3 will be raised to the power of what? 6 times 1/2 is basically going to be 3, right? And this is equal to, over here, my 2x plus 5 raised to the 1/3 power is raised to the 6th power. Again, 6 times a third would give me 2. So this is 2x plus 5 squared. Okay, so let me erase this. We're not going to need it anymore. And let me kind of scooch this up, give myself a little bit of room, because this guy will be kind of messy. Okay, so we know the formula for a binomial cubed. It's going to be the first guy cubed, so x cubed, plus you've got 3 times this guy squared, so x squared, times this guy to the 1st power. So this would be a 9 here. Then plus, you've got 3 times, this guy is now raised to the 1st power, and this guy is going to be squared. So 9 times 3 is 27. This would be 27x. And then lastly, plus this last guy 3 cubed, which is 27. Okay, so this is equal to, if I squared this guy, I would have 4x squared plus 2 times 2x times 5. So 2 times 5 is 10. 10 times 2 is 20. And then times x. And then lastly, plus 5 squared is 25. So kind of hard to fit that all on the screen, but let's go through and see what we can do. So we've got our x cubed, nothing to combine with that. I can subtract 4x squared away from each side of the equation. So that's gone. I can subtract 20x away from each side of the equation. So that's gone. And I can subtract 25 away from each side of the equation. So that's gone. So I'm going to have that x cubed plus 5x squared plus 7x plus 2 is equal to 0. So at this point, most of us don't know how to factor this yet. We haven't learned about the rational root theorem. We'll talk about that later on in the course. So I'm just going to go ahead and tell you that this will factor into x plus 2 times, over here you would have x squared plus 3x plus 1, this equals 0. So I'll just give you this. Later on in the course, we'll learn how to factor polynomials on the left side like this. For right now, we'll just take this as a given, and we're going to solve this by using our zero product property. So I could set x plus 2 equal to 0, and I know that if I subtract 2 away from each side, I would get x is equal to negative 2. So that's going to be one solution. Then my other solution, I would set x squared plus 3x plus 1 equal to 0. I can solve that with my quadratic formula because I can't factor this guy. So let's go ahead and label this 1 as the coefficient of x squared as a. Let's label this 3 as the coefficient of x to the 1st power as b. Let's label this 1 out here, this constant as c. So x is equal to the negative of b. b is 3. So the negative of 3 plus or minus the square root of b squared. So 3 squared is 9. And then minus 4 times a is 1, times c is 1 also. So 9 minus 4 is 5. Let's just write this as square root of 5 here, and this is over 2 times a is 1. So this is as simple as you can make this. You have negative 3 plus square root of 5 over 2, and then negative 3 minus square root of 5 over 2. So let's copy these, and we'll go back up. So for x equals negative 2, let's just plug in a negative 2 here and here. Very straightforward. Negative 2 plus 3 would be 1. Square root of 1 is 1. This is equal to 2 times negative 2 is negative 4. Negative 4 plus 5 is 1. The cube root of 1 is 1. So this guy definitely checks out. This is a solution, right? X equals negative 2. Now, for this guy right here, it's very, very tedious, especially since you have different kind of indexes here. So what I'm going to do is I'm going to approximate each root here, okay? So I'm going to say that x is approximately, if I did negative 3 plus square root of 5 over 2, I'm going to go ahead and approximate that to negative 0.382, okay? Then another one, I'm going to go x is approximately, we've got negative 3 minus the square root of 5 over 2. I'm going to say this is about negative 2.618, okay? So it's just easier if you use approximations here. You're going to see that they're very close to being equal, right, if they work, and then they won't even be close at all if they don't work, okay? So let's go ahead and plug this guy in for x. So negative 0.382. Let's plug that in for x as well. All right, so on the left side, 3 minus 0.382 is 2.618. So I would have the square root of 2.618. And if I approximate this, I can say it's about 1.62. Okay, about that. So let me kind of erase this, and I'll say on this side, it's approximately 1.62. So I'm looking for something on this side that's very close to that, okay? So 2 times negative 0.382 would be negative 0.764. So let's say this is negative 0.764, then plus 5. That would give me 4.236. So I would have the cube root of 4.236, and I could approximate this to 1.62 as well. So these sides are approximately the same when we use, again, these approximations. So that's enough for me to say that x equals negative 3 plus the square root of 5 over 2 is a solution. So I can check this, or I can kind of break these up, which would be better. I'll say x equals negative 3 plus square root of 5 over 2. Let me kind of erase this. This is a valid solution. So let me kind of bring this up. And let me check this one now. So let's erase this. So you get negative 2.618 plus 3. That's going to give you a 0.382. If you take the square root, you can say that's about 0.618. Okay? That's approximately what that's going to be. On this side, if I plug this in for x, you're going to see that you have a problem. 2 times this guy right here is going to give you negative 5.236. Well, when I add that to 5, I'm going to get a negative. The cube root of a negative is going to be a negative. This side's a positive, so it's not possible for this one to work. So you can reject the solution of x equals negative 3 minus the square root of 5 over 2. This guy is going to be extraneous, okay? So if you get in a situation like that, don't be afraid to use approximations. You can use that to see if your solution is going to work or not, right? We can immediately see that this guy doesn't work. This guy was very close, so you know if you plugged in the actual number, it would work. So this is an acceptable answer, and so is this one. So x equals negative 2, or x equals negative 3 plus square root of 5 over 2. In this lesson, we want to review solving radical inequalities. So in our last lesson, we reviewed the process used to solve radical equations. In this lesson, we're just going to build on that knowledge and review how to solve radical inequalities. So solving radical inequalities is not something that's hard, but it can be very, very tedious depending on the complexity of the problem. So before we kind of jump in and start looking at problems, there's a few things that we need to remember. So first and foremost, when we're working in the real number system, a radical with an even index, so a square root, a fourth root, a sixth root, so on and so forth, it's got to have a non-negative radicand. So something like the square root of negative 25, again, this is not real. Okay, this is not real. And I know we can use the imaginary unit I here to kind of get a solution, but we're not talking about the complex number system here. We're talking about just real numbers. Okay, so in the real number system, there's no number that we can square that would give us a result of this radicand here of negative 25. So this is not real. So to guard against this, taking the square root of a negative, when we have a variable involved, let's say we had something like the square root of x, we've got to set that variable as greater than or equal to 0, right? To guard against a square root of a negative, okay? Or if you had something like the fourth root of x, well, again, x has to be greater than or equal to 0. Because again, if you plugged in a negative here or here, you can't do that, right? You don't want the square root of a negative. You don't want the fourth root of a negative. You don't want the even root of a negative. Now, if you get something more complex, let's say you had the square root of something like x minus 7. Well, here, you need to make sure that this radicand ends up as a non-negative value. So what you do is you take your expression and you're going to set it as greater than or equal to 0. This is going to give you any domain restrictions that you would have. You're going to find the allowable values for x by doing this. So I'm going to add 7 to both sides of the inequality, and I'm going to find that x must be greater than or equal to 7. Okay? So if x is 7, we're okay, because 7 minus 7 is 0. Square root of 0, that's fine. That's just 0. But if x is something less than 7, well, then we have a problem, right? If I plugged in 6 there, 6 minus 7 would be -1. Square root of -1, again, is not real. So when you're working with, again, square roots, fourth roots, sixth roots, so on and so forth, you need to make sure that if it's an expression under there with a variable, you set that guy as greater than or equal to 0, and you solve it, and that's going to give you any domain restrictions that you would have. Again, for this example, we found that x must be greater than or equal to 7. Now, if we're working with a radical with an odd index, you don't have this issue, right? We know that if we had something like the cube root of -8, this is a real number. This is -2, right? Because I can raise a negative number to an odd power and get a negative, okay? So the cube root of -8 is -2. Or the fifth root of, let's say, -243 would be -3, right? Because -3 to the fifth power is -243. So if I got something like, let's say, the cube root of x, this is valid for any real number, right? So I can plug in anything for x. You can say x is any real number. Okay? So with an odd index, you don't have those restrictions. All right. Let's jump in and look at a problem. So we have that 3 times the square root of x plus 3 plus 13 is greater than or equal to 16. So the first thing I would do with this type of problem is find the domain restriction. So we would take this expression here for our radicand, this x plus 3, and we would say it has to be greater than or equal to 0, right? This is what we're going to accept as values for x. So let's subtract 3 away from both sides of the inequality. We're going to find that x must be greater than or equal to -3. Again, that makes sense because if I plug in a -3 here, -3 plus 3 is 0, so you're good there, right? Square root of 0, you're fine. That's 0. If you plug in something less, though, you've got a problem. If you plugged in a -4, -4 plus 3 is -1. Square root of -1, again, is not real. So let's state this again as our domain restriction. X must be greater than or equal to -3. So if we solve this guy and we get something that violates the domain, we've got to kind of exclude that. Okay, and we'll get to that in a minute. So now let's talk about solving the inequality. So the way I'm going to do this is I'm going to replace this inequality symbol with equals, and I'm going to solve the resulting equation. So I'm going to have 3 times the square root of x plus 3, then plus 13 is equal to 16. Okay, so I'm going to solve this. I'm going to get my boundary, okay, and then I'm going to look at my number line, and I'm going to test each side of the boundary, okay? So how do we solve this? We know that our goal is to isolate the radical, right, to start. So I'm going to subtract 13 away from each side of the equation, and we know that this is going to cancel. We'll have 3 times the square root of x plus 3 is equal to 16 minus 13 is 3. So now, to isolate the radical, all I want to do is divide both sides of the equation by 3. And that's going to give me what? Let me kind of scroll down and get some room going. That's going to give me that the square root of x plus 3 is equal to 1. Now that I have my radical isolated, I can square both sides to get rid of it. So I'm going to square this side, and I'm going to square this side. Now remember, when you square both sides of an equation, you might end up with extraneous solutions. Okay, so we got to make sure we check. So this guy is going to end up as x plus 3 is equal to 1. Okay, so to solve this guy, I subtract 3 away from each side of the equation, and I end up with x is equal to -2. So this is my boundary. Okay, if I plugged in a -2 for x, the left side is going to end up as 16. So let's see that real quick. So let me write this down here as my boundary. X is equal to -2. So again, if I plug that in here, -2 plus 3 is 1. Square root of 1 is 1. So you basically have 3 times 1, which is 3, plus 13, which is 16. So you would get that 16 is greater than or equal to 16. Again, if this was an equation, you'd see that you have a true statement, right? So we know that this solution here is not extraneous, okay? But consider the fact that you get 16 is greater than or equal to 16. So we know that a value of -2 works as a solution for the inequality, so it's going to be included. Now, what you need to do is test values on each side of -2 to see if they work. All right, so we come down to the number line, and essentially we know that x equals -2 is our boundary, okay? Let me just label this for the first problem. So this is our boundary. Again, some people call them critical values, critical points, whatever term you want to use. So at -2, I'm just going to put a vertical line here. So to the left of -2, we have values that are less than -2. To the right of -2, we have values that are greater than -2. So we want to see what's going to work in the original inequality. So we have 3 times the square root of x plus 3. Then plus 13 is greater than or equal to 16. Now, this is subject to our constraint, right? Our domain restriction that specifically told us that x had to be greater than or equal to -3, okay? So really, you could make another interval here if you wanted to. You don't have to, but you could make another one just to visibly say that, hey, anything to the left of -3 is not going to work. So if it shows up as a solution, you've got to reject it. So I'm just going to label this as interval A. I'm going to label this as interval B, and I'll label this as interval C, just to keep track of what's going on. So what we're going to do here is we're going to test a value in interval B and C only. We don't need to test stuff in interval A. That's an automatic rejection zone. We'll put a false there, an F for that, because again, it violates the domain. So between -2 and -3, so I'm going to pick a value of -2.75. So -2.75 plus 3 would be 0.25. So I would have 3 times the square root of 0.25 plus 13 is greater than or equal to 16. So what's the square root of 0.25, or what's the square root of 1/4? Well, it's going to be 1/2. So this would be 3 times 0.5, or 3 times 1/2, plus 13 is greater than or equal to 16. And again, 3 times 1/2 is just 3 halves. So you'd have 3 halves plus 13 is greater than or equal to 16. Without going through and getting a common denominator and all that stuff, you can see that's not going to work, right? This is basically going to be 13 plus 1.5, which is 14.5. That's not greater than 16, and that's not equal to 16. So things in interval B are not going to work. We'll put this as false also. So what about things in interval C? What about things that are greater than -2? We already know that -2 works because it's a non-strict inequality, and we tested it earlier. But what about things that are greater than -2? Does that work? So for interval C. Well, let's go ahead and try to make this easier on ourselves, a value of 1. So we'll plug that in. 1 plus 3 is 4. Square root of 4 is 2. So you'd have 3 times 2, which is 6, plus 13, which is 19. So you'd have 19 is greater than or equal to 16, which is true. So things in interval C will work. So that's where we're going to have our solution region. So interval C is anything greater than -2. And again, because this is a non-strict inequality here, and we tested it, right? If we plug in a value of -2, -2 gives us a value of 16 on the left. We'd have 16 on the right. 16 is greater than or equal to 16. That's true, right? So -2 does work. So we would say that our solution here is x is greater than or equal to -2. And the great thing here is that it doesn't violate our domain, right? Our domain says that it has to be greater than or equal to -3. We're greater than or equal to -2, so we're basically good to go. So in interval notation, we'd put a bracket, a -2, a comma, an infinity symbol, and a parenthesis. And then graphically, you can kind of follow that same pattern. We'll put a bracket at -2, and we'll just shade everything to the right. Okay, and that'll be our solution. All right, let's take a look at another one. So we have the square root of x plus 12 minus the square root of x is greater than 2. So since we have 2 square roots involved, we're going to think about 2 different domain restrictions, and we got to go with the stricter one. Okay, so for this one, I would set x plus 12 and say that's got to be greater than or equal to 0. And then for this one, I would say x has to be greater than or equal to 0. So for this one, I subtract 12 away from each side. I find that x has to be greater than or equal to -12. For this one, we know that x just has to be greater than or equal to 0. This one is more restrictive. Okay, so I'm going to go with this one as my domain, because if I got a value that's between -12 and 0, it wouldn't work, right? It might work in this one, but it's not going to work in that one. Okay, so you've got to go with the stricter one. So what we're going to say is that x has to be greater than or equal to 0. So let's just write that over here. we'll say x has to be greater than or equal to 0. All right, now to solve this, I'm just going to replace this with equals. So I'm going to have the square root of x plus 12 minus the square root of x is equal to 2. All right, so I'm going to isolate one of the radicals. I have 2 involved, so you can isolate either one first. Doesn't matter. It's probably going to be easier to isolate this one. So what I'm going to do is I'm going to add the square root of x to both sides of the equation. And so on the left, I'm going to have the square root of x plus 12. And this is going to be equal to, on the right, I'm going to have the square root of x and then plus 2. So now I'm going to square both sides. Let me get some room going. I'm going to square this side, and I'm going to square this side. So on the left, I'll just have x plus 12. On the right, remember, I have to expand this. So you can use FOIL, or you can use your special products formula. So I would square this first guy. So the square root of x squared is x. And then plus, you'd have 2 times this guy times this guy. So 2 times 2 is 4. Then times your square root of x. Then plus the last guy, 2 squared, which is 4. So I still have a radical involved, so I need to make sure that I clear that guy out. So I want to isolate that again. So what I'm going to do first is just kind of simplify or clean things up. I have an x on each side. If I subtracted that away from each side, it would cancel everywhere. And basically what I'm going to do is subtract 4 away from each side. So I'm going to have that 8 is equal to 4 times the square root of x. Again, if I want to isolate the radical, let's divide both sides of the equation by 4. And let me kind of get some more room going. So this cancels with this and gives me a 2. This cancels with this and gives me a 1. You've got 2 is equal to the square root of x. If we square both sides, we're going to get that 4 is equal to x. Okay, or x equals 4. So let me erase everything. All right, so we found that our boundary was x equals 4. Again, you can check this. If you plug in a 4 there and there, 4 plus 12 is 16. Square root of 16 is 4. Then minus the square root of 4 is 2. Again, I replace this with equals. So 4 minus 2 is 2. 2 equals 2. So that works out, right? We don't have an extraneous solution. Now, this is a strict inequality, so 4 does not work as a solution. Okay, so we know that. What we want to do is go to the number line, and we want to test values on each side of 4 to see what works and what doesn't. Now, we know that we have a domain restriction here that x has to be greater than or equal to 0. All right, so we found that our boundary was at x equals 4. All right, so here's 4 on the number line. So I want to test values on each side of this. But remember, x needs to be greater than or equal to 0. This is our domain restriction. So if I test values on the left side of 4, what would I get? So let's go ahead and rewrite our inequality. So we have the square root of x plus 12, and then minus the square root of x. And again, this was greater than 2. So I can choose anything I want with the exception that it has to be greater than or equal to 0, right? So it's got to be kind of to the right or equal to that 0 there. So let's just go ahead and pick 1. So if I plugged in a 1 there and there, what would I get? Well, here on the left, you'd have square root of 1 plus 12, which is square root of 13. Then minus square root of 1 is 1. This should be greater than 2. So the square root of 13 is about 3.6, okay? If I subtracted away 1, you'd have about 2.6, so that would work. That would be greater than 2. So basically, values to the left of 4 work, with the exception of they have to be greater than or equal to 0. So we can say that anything, let's call this interval A. Let me kind of divvy this up, and let's call this interval B. So anything in interval A that's to the left of 0 doesn't work, right? Because it violates our domain. Then anything in interval B is going to work, right? Because it's greater than or equal to 0, but less than 4. So that's going to be good to go. What about anything in interval C? So that's going to be anything that's larger than 4. So let's test that out. So let's erase this, and I can check a value over here. Let's just choose the value 9. Plug that in there and there. So 9 plus 12 is 21. So you'd have the square root of 21, then minus the square root of 9 is 3. Is that greater than 2? Well, the square root of 21 is about 4.58. Okay, that's an approximation. If I subtracted away 3, I'd have about 1.58. So that's not greater than 2, so this would be false. So we have our solution here. We found that values in interval B will satisfy the inequality. So essentially, it's anything that includes 0 up to but not including 4. So x can be greater than or equal to 0 and less than 4. Okay, anything in that range. In interval notation, again, you put a 0 next to a bracket and then a 4 next to a parenthesis. And then graphically, we would put a bracket at 0 and we put a parenthesis at 4 and we would shade everything in between. All right, let's take a look at the next example. So we have the square root of 4x minus 1 is greater than the square root of x minus 5. So for this guy, again, I've got two domain restrictions that I need to consider. I've got that 4x minus 1 has to be greater than or equal to 0. And let's do that first. So let's add 1 to each side of the inequality. You'd find that 4x is greater than or equal to 1. Divide both sides of the inequality by 4. You'd find that x has to be greater than or equal to 1/4. So here, this one's going to be more restrictive, right? So here, if I set x minus 5 is greater than or equal to 0, I add 5 to both sides of the inequality. I find that x has to be greater than or equal to 5. So again, this one's more restrictive, so that's going to be our domain. So x has to be greater than or equal to 5, okay? Let's erase all this now that we know what we're looking for. And let's replace this inequality with an equals. So we would have the square root of 4x minus 1 is equal to the square root of x minus 5. Let me make that a little better. So both radicals are isolated here. So let's just square both sides. And I'll have my 4x minus 1 is equal to x minus 5. Let's add 1 to both sides of the equation. You'll get that 4x is equal to x. And then negative 5 plus 1 is going to be negative 4. Let's subtract x away from each side of the equation. We kind of do this over here. We'd end up with 3x is equal to negative 4. Divide both sides of the equation by 3. You get x is equal to negative 4/3. Okay, so let's erase this. So what happens is this guy is extraneous, and you can immediately see that it's not going to work if you plug it in here because it's going to violate your domain, right? X has to be greater than or equal to 5. So you can kind of get rid of this at this point. A lot of people would stop and say, okay, well, there's no solution, but that's not actually true either. Okay, so here's where you've got to kind of go down to the number line and consider things. So we know that this guy is only valid for values of x that are greater than or equal to 5. But I want you to think about something. You have the square root of something, and then you have the square root of something. You're saying, where is the square root of this expression greater than the square root of this expression? Well, if I'm doing the same thing to each side, again, you could just consider where is 4x minus 1 greater than x minus 5. If you solve this, you're going to end up with the same thing you got when you solve the equation. You're going to end up with x is greater than negative 4/3, right? When we solved it, we got x is equal to 4/3. But essentially, as long as x is a value that's larger than negative 4/3, then the right side here is less than the left side, or you can say the left side is greater than the right side, okay? So that means that for values where it's valid in the domain, where x is greater than or equal to 5, the left side should be greater than the right side. So we can check that. Let's go down to the number line. And again, the domain here is that x is greater than or equal to 5. So at 5, I'm just going to put a little border. And I'm going to say that we can test something to the right of 5. We know anything to the left of 5 doesn't work because it violates the domain. So I'll call this interval A and this interval B. And I'll say that in interval A, nothing works, okay, because it violates the domain. So for interval B, I can just choose something. Let's just choose something like 6, and we can check that. So remember, we had that the square root of 4x minus 1 is greater than the square root of x minus 5. If I plug in a 6 for x, I'd have 4 times 6, which is 24. 24 minus 1 is 23. So the square root of 23 is greater than 6 minus 5 is 1. Square root of 1 is 1. Okay? So what's the square root of 23 if I approximate that? Well, it's going to be about 4.79. So that's clearly greater than 1. So in this interval B, things are going to work. Okay? So this is going to be our solution. It's basically that x is going to be greater than or equal to 5. Okay? So we'll say x is greater than or equal to 5. That's both our domain restriction and our solution for the inequality. And graphically, I can just put a bracket at 5 and just shade everything to the right. In an interval notation, I can put a bracket of 5, comma, and then infinity, okay, in a parenthesis. All right, let's look at one with a cube root involved. So these are a lot easier. When you have a cube root, you don't have a domain restriction. So I don't have to start by saying x minus 7 is greater than or equal to 0. This value here, this radicand can end up being whatever. Okay, it can be negative, it can be 0, it can be positive. Remember, in the real number system, you can take the cube root of a negative number. Okay, so you're good to go there. So all I'm going to do is just solve this guy. So let's go ahead and replace this guy with an equals and solve. So 2 times the cube root of x minus 7 plus 6 is equal to 2. Let me again isolate the radical. So let me subtract 6 away from each side of the equation. That'll cancel. You have 2 times the cube root of x minus 7 is equal to negative 4. Let me divide both sides by 2 so I can isolate the radical. Let me kind of move this up here. You'll have the cube root of x minus 7 is equal to negative 4 over 2 is negative 2. So to get rid of the radical, I'm going to cube both sides of the equation. I'm going to find that x minus 7 is equal to negative 8. Let me add 7 to both sides of the equation, and I'll find that x is equal to negative 1. So again, that's the boundary. So let me erase all this. X equals negative 1. Again, that's the boundary. And I don't have a domain restriction. So let me go down to the number line. So here's negative 1. So basically, you're going to have 2 scenarios. You're going to have this interval A and this interval B. Okay, you don't have any domain restrictions. So just pick something in interval A and test it. So again, we have 2 times the cube root of x minus 7 plus 6, and this should be greater than 2. Okay, so something less than negative 1, we can pick, let's say negative 20. So negative 20 minus 7 is negative 27. So the cube root of negative 27 is going to be negative 3. So 2 times negative 3 is negative 6. So you'd have negative 6 plus 6 is greater than 2, which is false. So I know values in interval A don't work. So this is going to be false. Then what about values in interval B? So let's choose 8. So I'll plug in an 8 there. 8 minus 7 is 1. Cube root of 1 is 1. So 2 times 1 is 2. Plus 6 is greater than 2. You get 8 is greater than 2, which is true. So for interval B, it's true. So anything larger than negative 1 would work. So we can say our solution here is that x is greater than negative 1. All right, so in interval notation, you've got negative 1 comma infinity, again with a parenthesis next to each. Let me erase this. Graphically, I'm going to put a parenthesis at negative 1. I'm just going to shade everything going to the right. In this lesson, we want to continue to talk about solving radical inequalities. So in the last lesson, we started talking about solving radical inequalities. In this lesson, we're just going to have a follow-up to that. We're going to have basically a part 2. We're just going to look at some more challenging, or you could say more tedious problems. So the first one we're going to start with is pretty easy. We have the fourth root of 2x minus 5 is less than or equal to 1. Now, in our first lesson, we didn't see anything with a fourth root. We just worked with a square root and a cube root, okay? But with the fourth root, again, it's an even number here for the index. So you've got to remember, in the real number system, if I have an even index on my radicand, or the number under the radical symbol, cannot be negative, okay? It can be 0 or something positive. So when we set this up, the first thing we want to do is we want to take our radicand, which in this case is 2x minus 5, and we want to say that that needs to be greater than or equal to 0, okay? So I'm going to add 5 to both sides of this inequality, and we're going to find that I have 2x is greater than or equal to 5. Let me divide both sides by 2, and I'm going to find that x needs to be greater than or equal to 5 halves. So in other words, if I plug in 5 halves for x, I will get 0 there, right, for my radicand. I can take the fourth root of 0, that's just 0. That's okay. But if I plug in something less than 5 halves, I'm going to have a problem, right? Because this guy, the radicand would end up being negative. I can't, in the real number system, have the fourth root of a negative value because it doesn't exist, okay? There's no number that I can raise to the fourth power and end up with a negative value because, again, an even number of negative factors will always give you a positive result, okay? So let me erase this, and I'm just going to write this up here. So we have that x is greater than or equal to 5 halves. Again, that's my domain restriction. So the idea with this is if I get a solution for my inequality and it violates the domain, I've got to reject it, okay? So how do we solve the inequality? Well, one way that we can do this, we can replace the inequality symbol with equals, and we could solve that to get our boundary, okay? So we can say that we have the fourth root of 2x minus 5, and that's equal to 1. Very easy to solve this equation. My radical is already isolated on the left. So to get rid of the radical, since my index is a 4, I'm going to raise this to the 4th power, and then to make it legal, I'm going to raise this to the 4th power. So this is going to cancel here, and then I'm going to have my radicand, right? So just my 2x minus 5. This will be equal to 1 to the 4th power is obviously 1. Now it's very easy to solve from this point. We just add 5 to both sides of the equation. So that's going to cancel. And we'll get that 2x is equal to 1 plus 5 is 6. One last step. We want to isolate x. So I'm going to divide both sides by 2. And I'm going to find that x is equal to 6 over 2 is 3. So I'm going to put x equals 3 here. And that's going to be my boundary. Okay. So let's take these two values here down to the number line, and we're going to test a value on each side of 3. Okay, 3 is the boundary, so we're going to test the value on the left side of 3, something less than 3, and I'm going to test something on the right side of 3, something greater than 3. But you have this restriction here. Remember, x has to be greater than or equal to 5/2, so we got to keep that in mind. So let's erase all this, and before I go down there, I want to show you one thing real quick. The first thing is that 3 works as a solution in this inequality. This is non-strict here. If I plug a 3 in, 2 times 3 is 6, 6 minus 5 is 1, the 4th root of 1 is 1, so you get that 1 is less than or equal to 1, which is true, okay? So this guy right here works as a solution. So let's go down to the number line. So again, our domain restriction is that x has to be greater than or equal to 5/2, and then our boundary is that x equals 3, which again works as a solution. So here's 3. Let me put a vertical line there. And then 5/2 as a decimal is 2.5. So let's put something right there and say this is 5/2. So I can also put a vertical line there. Now, you can split this into regions. Okay, this is very easy to do for reference sake. So anything to the left of 5/2, I'm just going to call that region A or interval A. Anything between 5/2 and 3, and it's a tight window, I'm going to call that interval B. Okay, I'm just going to put an arrow there because I can't really fit my letter there. And then anything to the right of 3, I'm going to call that interval C. So for interval A, anything to the left of 5/2, we know that's an automatic rejection, right? Because it violates the domain. So I'm going to put an F there for false. Now, for interval B, I need to test the value. So my original inequality was the 4th root of 2x minus 5 is less than or equal to 1. So something between 2.5 and 3, I could do 2.75. So let me get some room. I'll come back up. So if I plugged in a 2.75 there for x, what would I have? I would have the 4th root of 2 times 2.75, which is 5.5. So you'd have 5.5 minus 5 is less than or equal to 1. So then I have the 4th root of 0.5 is less than or equal to 1. Now, if I took the 4th root of 0.5, basically I could approximate that to be about 0.84, okay? About 0.84. So if we had about 0.84, that would be less than 1, okay? So that would be a true statement. So let me erase everything, and I'm going to say that things in interval B work, okay? Let me slide this down just a little bit, and I'm going to put interval B right here, and I'll say that's true, okay? So anything between 5/2 and 3, including both, okay? 3 is included and 5/2 is included because essentially it's anything that's less than or equal to 3. So it's going down to and including 5/2 because that's part of your domain. But anything to the left of 5/2 isn't going to work because it's not included in the domain. So what about things in interval C? So things that are greater than 3. Well, you can test anything you want. So let's just pick 4 and plug that in. Again, I'm just going to slide down for a minute. So if I plugged in a 4 there, what would I get? Well, 2 times 4 is 8. 8 minus 5 is 3. So you'd have the 4th root of 3 is less than or equal to 1. So if I approximate the 4th root of 3, I'm going to get about 1.32, which is larger than 1. Okay, so this is false. So this is false. So things in interval C don't work, and we'll say that for interval C, it's false. So I have my solution. Again, x is going to be any value that's 5/2, and including 5/2, going up to and including the number 3. So let me erase all of this. I don't need it anymore. So again, x is greater than or equal to 5/2 and less than or equal to 3. All right, so in interval notation, I'm going to put a bracket next to 5/2. Then comma, I'm going to put a bracket next to 3. And then graphically, Again, let me put my 2.5 or my 5 halves back on the number line. So that's going to be right there. Again, this is my 5 halves. This is going to be a tight window, but I'm going to put a bracket here. I'm going to put a bracket here. I'm just going to shade in between. So again, it's from 5 halves or 2.5 up to and including 3. So the 5 halves is included and the 3 is included and all the values in between. All right, let's take a look at another one. So for this one, we have the square root of 2x plus 6 is greater than x minus 1. Remember, if you have a square root involved, or again, a fourth root like we just saw, or a sixth root, any even root, then you need to figure out what the domain restriction is going to be. So in this case, 2x plus 6 has to be set as greater than or equal to 0. So 2x plus 6, my radicand there, again, has to be greater than or equal to 0. Let me subtract 6 away from each side of the inequality. That's going to give me that 2x needs to be greater than or equal to negative 6. We'll divide both sides by 2, and we'll find that x needs to be greater than or equal to negative 3. So that's my domain restriction. Again, if I get something that's less than negative 3, I've got to reject it, okay? So let me go ahead and erase this, and I'll slide this up. Now, let's go about solving our inequality. Again, the method I'm going to use, I'm just going to replace this with an equals, and I'm going to solve the resulting equation. So we're going to have the square root of 2x plus 6 is equal to x minus 1. So again, the radical on the left side is already isolated, so I can go ahead and just square both sides. So I'm going to square this side, and I'm going to square this side. So what's going to happen over here is this is going to cancel with this. I'll just have my radicand. So the left is 2x plus 6. On the right side, remember, I have to expand this, okay? So x minus 1, that quantity squared, you can use your formula. It's the first guy squared, so x squared. Then you have a minus there, so it's going to be minus 2 times this guy times this guy. So 2 times x times 1 is 2x. Then plus the last guy 1 squared, so plus 1. Okay, so what I'm going to do, since I'm going to end up with a quadratic, I'm just going to go ahead and move everything on the left over to the right. So my left is going to be 0, okay? So what I'm going to do, I'm going to subtract 6 away from each side of the equation. So that's going to cancel. And I'm going to subtract 2x away from each side of the equation. So that's going to cancel. So the left side is now 0. So I'm going to have that 0 is equal to x squared. Negative 2x minus 2x is minus 4x. And then 1 minus 6 is going to be minus 5. So you can flip this around if you want. I know most of you, including myself, like the variable parts on the left. So you can say x squared minus 4x minus 5 is equal to 0. That's perfectly legal. So let me scroll down a little bit more. This is one that we can solve using factoring. So that's what I'm going to do. For the left side, I can factor that by putting an x here and an x here. And they give me two integers whose sum is negative 4 and whose product is negative 5. Well, negative 5 can only come from 1 times negative 5 or negative 1 times positive 5. So what I'm looking for is positive 1 and negative 5. So if we solve this using our zero product property, we would set x plus 1 equal to 0. Of course, that would give us a solution of x is equal to negative 1. And we would set x minus 5 equal to 0, and that would give us a solution of positive 5. Now, one of these is going to be extraneous, okay? So let me erase everything, and we're going to check both of these, and I'll show you which one's extraneous. All right, so again, we found that the solutions for this equation are x equals negative 1 and 5. If you plug in a 5, you're fine. So if I plugged in a 5 there and also there, I'd be okay. 2 times 5 is 10. 10 plus 6 is 16. The square root of 16 is 4. Over here, 5 minus 1 is 4, so this one is good to go. But with negative 1, you're going to have a problem. Okay, with negative 1, you have an issue. If you plug that in here and here, 2 times negative 1 is negative 2. Negative 2 plus 6 is positive 4. So you'd have the square root of 4, which is 2, and that's equal to negative 1 minus 1 is negative 2. So obviously this is false. Okay, this is false. So this guy needs to be rejected. Okay, it's an extraneous solution. So your boundary here is 5, and basically your restriction is that x needs to be greater than or equal to negative 3. So let's take this information down to the number line. So again, my inequality is the square root of 2x plus 6. And again, this is greater than x minus 1. My restriction on the domain is that x needs to be greater than or equal to negative 3. And my boundary occurs at 5. So x equals 5 is the boundary. So on the number line, 5 is here. Let's just draw a vertical line there. And -3 is here. So let's draw another vertical line here. So we know anything to the left of -3 doesn't work. So let me go ahead and put this as interval A. Again, anything to the left of -3. And I'm just going to put that this is an automatic rejection, right? So an F or false. Then you have anything between -3 and 5. And then you have anything that's larger than 5. So this area will be called B, and this one will be called C, okay? So let's start out by testing something in interval B. So again, this is between -3 and +5. So if I plugged in, let's say, I don't know, how about 0? So let's plug that in there, and see what we get. So we know that 2 times 0 is 0, so you'd have basically the square root of 6 is greater than 0 minus 1 is -1. Well, we don't need to know what the square root of 6 is. We don't need to even approximate it because this is a positive number. Of course, it's going to be greater than a -1 because a positive number is always greater than a negative, okay? So this is true. So let me erase this. We'll basically say that things in interval B will work. So for interval B, it's going to be true. So it's going to be anything that's less than 5 going down to and including -3 because -3 is still in the domain, okay? Now, what about things in interval C? Do they work? To make this easy on ourselves, let's choose 29. So I could plug that in for x there. 2 times 29 is 58. Then if I add 6, I'd get 64. So what you'd have is the square root of 64 is greater than 29 minus 1, which is 28. I know the square root of 64 is 8. 8 is not greater than 28. That is a false statement. So things in interval C will not work, so I'll put an F there for false. All right, so we have our solution now. So anything in interval B will work. So again, we've got to be specific here. It's anything less than 5, but because we have this domain restriction that anything less than -3 doesn't work, you basically say that x has to be greater than or equal to -3, but less than 5. Okay, so -3 is included, 5 is not. All right, so in interval notation, I can say that, again, -3 is included by putting a bracket there, and then comma, you have a 5, and then a parenthesis. And then graphically, you erase this. So again, at -3, I'm going to have a bracket. At 5, I'm going to have a parenthesis. I'm just going to shade everything in between. All right, let's take a look at one to wrap up the lesson that's pretty tedious. So we have the square root of x squared minus 5x plus 6 is less than x plus 3. So what makes this problem tedious is that you have a quadratic inequality that you're going to need to set up to find your domain restriction, right? Because you have x squared minus 5x plus 6 that's underneath the square root symbol. So we need to set this as greater than or equal to 0, okay? So this guy right here, again, it's a quadratic inequality. At this point, we know how to solve this. We're going to replace this guy right here with equals. And we're going to solve x squared minus 5x plus 6 equals 0. This will give us our boundary, or again, critical values. And then we're going to test values on each side of that. Okay, so we're going to set up intervals and test just like we've been doing. So what I'm going to do is solve this by factoring. I know that this guy would be x and this guy would be x. Two integers that sum to -5 and give me a product of +6 would be -2 and -3. Right? -2 plus -3 is -5. -2 times -3 is +6. So if I solve this equation, I would find that x is equal to what? X minus 2 is equal to 0. That has a solution of x equals +2. If x minus 3 is equal to 0, that has a solution of x equals 3. Okay, so 2 and 3 are going to be my boundaries. So let's go down to the number line. So again, the critical values or the boundaries, x equals 2 and 3. So here's 2, here's 3. And again, we're going to set up intervals. So anything to the left of 2 is A, anything between 2 and 3 will be B, and anything greater than 3 will be C. So again, you've got A, B, and C. So let's test some values. So again, we've got x squared minus 5x plus 6 is greater than or equal to 0. So let's start out by testing 0. That's something in interval A. We know that that would basically mark out this guy and this guy. So it would have 6 is greater than or equal to 0, which is true. So for interval A, things work. That's true. What about interval B? Well, I can take something like 2.5. That's between 2 and 3. So 2.5 So if I plugged in a 2.5 there and there, what would I get? Well, 2.5 squared is 6.25. Then if I subtract away 5 times 2.5, 5 times 2.5 is 12.5. Then if I add 6, is this greater than or equal to 0? Well, no, it's not, because 6.25 plus 6 is going to be 12.25. So 12.25. And if I subtract away 12.5, I'm going to get negative 0.25. So that's not greater than 0, and it's not equal to 0, because obviously it's a negative, and so it's not going to be greater than 0. Okay, so let's erase this. We're going to say things in interval B don't work. Okay, so let's go back up. And so we'll say things in interval B, again, between 2 and 3, those don't work. So that's going to be false. Then lastly, let's check something in interval C. So let's just pick 4. That's easy to work with. So I'll plug in a 4 there and there. So 4 squared is 16. And then minus 5 times 4 is 20. And then plus 6, is this greater than or equal to 0? Well, 16 plus 6 is 22. 22 minus 20 is positive 2. So you'd have that 2 is greater than or equal to 0, which is true. So for interval C, or region C, or whatever you want to call it, this is going to be true. So I've found my domain. Okay, I've found my domain. Basically, we can say that x needs to be what? It needs to be greater than or equal to positive 3. And the or equal to is because I had a non-strict inequality, so the endpoints or the boundaries are going to be included. Then or x needs to be less than or equal to that value of 2. So the values that don't work in our inequality are going to be things between 2 and 3. 2 works, 3 works, but it's got to be less than 2 or equal to 2, or greater than 3 or equal to 3, but anything in between will not work. So I'm going to leave this here because we're going to work on this later on. So this will just stay here. But I'm also going to copy it and bring it up for reference sake. We're done with this information. We can erase it. So to solve the inequality now, I know my domain. I'm just going to replace that with equals. So I'm going to have that the square root of x squared minus 5x plus 6 is equal to x plus 3. So to solve this, my radical is already isolated on the left. So I'm just going to square both sides. So this is going to cancel with this, and I'll have my radicand of x squared minus 5x plus 6 is equal to, again, you've got to expand this, okay? So this is going to be x squared plus 2 times x times 3, which is 6x, plus 3 squared, which is 9. Now I have x squared on each side. I can subtract that away from each side. Again, if you see the same thing on each side, you can just get rid of it. So I can cancel this and this. So on the left side, I have negative 5x plus 6. On the right side, I have 6x plus 9. So let's move all the variable terms to one side, all the numbers to the other. So let me subtract 6 away from each side. And let me subtract 6x away from each side. So negative 5x minus 6x is negative 11x. This is equal to, over here, 9 minus 6 is 3. So to get my solution for x, I'm going to divide both sides by the coefficient of x, which is negative 11. So I'm going to find that x is equal to negative 3/11. Okay, negative 3/11. So let me erase everything. All right, so x is negative 3/11. That's our boundary. And again, the restrictions on the domain, x has to be greater than or equal to 3 or less than or equal to 2. So let's go to the number line with this information. So again, we found that x was equal to negative 3/11. So that's our boundary. So negative 3/11 as a decimal is a repeating decimal. It's negative 0.27, where that 27 repeats forever, okay? So if we wanted to put this on the number line, we could go about right here and just say that this represents negative 3/11. So I'm going to put a vertical line there, okay? And then again, things need to be greater than or equal to 3, so I can put a vertical line here. And things need to be less than or equal to 2, so I can put a vertical line here. So if I called this to the left of negative 3/11 interval A, I could call between negative 3/11 and 2 interval B. I could call between 2 and 3 interval C. And I could call anything larger than 3 as interval D. Now, we know that things in interval C, okay, between 2 and 3 don't work because they violate the domain. Okay, so I have A, B, C, and D. Again, this is false. It doesn't work. So let's choose a value in interval A and see if that works. So again, our inequality was the square root of x squared minus 5x plus 6. Again, this had to be less than x plus 3. So I'm going to pick a value of, let's say, -1. That's pretty easy to work with. So let me scroll down to get some room going. We'll come back up. So if I plugged in a -1 there, and there, and there, what would I get? Well, you'd have -1 squared, which is 1. And then -5 times -1 is plus 5. And then you'd have plus 6. So you'd have the square root of basically 12, right? 1 plus 5 is 6. 6 plus 6 is 12. So the square root of 12 could be simplified as 2 times the square root of 3, right? Because 12 is 4 times 3. 4 is a perfect square. So you could pull out the kind of 2 from that. So you would have 2 times the square root of 3, okay? So this is less than -1 plus 3 is 2. Well, that's going to be false. If you do 2 times the square root of 3, you're going to get about 3.46, and that's clearly not less than 2. So things in interval A don't work, okay? Those are going to be false. So for interval A, I'm going to put an F for false. Okay, what about things in interval B? So this is between -3/11 and, again, 2. So let's think about the number 0. That's easy to work with. So let's go ahead and plug that in for x. So 0 squared is 0. Then -5 times 0 is 0. So you basically just have your square root of 6 there. And that's less than, if you have 0 plus 3, that's 3. So the square root of 6 is, again, about 2.45, you could say. So that's going to be less than 3. So values in interval B are going to work. So let's erase this. We'll come back up. So we'll put this one as true. Okay? So anything in interval B is going to work. So anything larger than -3/11 is going to work. Okay, -3/11 won't work. So that's going to include 2, because, again, 2 is in the domain. So we're good to go there. Now, you can test something in interval D just to be safe, but essentially it's going to work, right? Because this is basically telling us that anything larger than -3/11 is going to be a solution, with the exception of the numbers that violate the domain, which, again, is anything between 2 and 3. But let's take something from interval D. Let's just take 4 and see if that works, just to be safe. So I plugged in a 4 there, and there, and there. What would I get? All right, so what I'd have here is the square root of 4 squared is 16. Then minus, you have 5 times 4, which is 20. Then plus 6, and this is less than 4 plus 3, which is 7. 16 minus 20 is -4. -4 plus 6 is 2. So you'd have the square root of 2 is less than 7. That's obviously true. So things in interval D will work. Okay. So let me erase all this. We're ready to put our solution together. Okay, so basically anything to the left of -3/11 doesn't work. We know that. Then anything greater than -3/11 will work. But you have this restriction here, basically where between 2 and 3, it's not part of the domain. So you just have to exclude between 2 and 3. But 2 and 3 itself are in the domain, so those are included. Okay, so x has to be greater than, and strictly greater than, -3/11. And less than or equal to 2, or x could also be greater than or equal to +3, okay? So again, 2 and 3 are included, and -3/11 is not included. So let me erase all of this. We don't need it anymore. So in interval notation, it's the union of these two sets here. So I would have a parenthesis next to -3/11, and then comma, you'd have a 2 and then a bracket. And the union with, you'd have a bracket next to 3, and this goes out to +infinity. So again, use a parenthesis with infinity. So let me write -3/11 in, again, right there. So this is -3/11. And again, I'm going to put a parenthesis there. And at 2, I'm going to put a bracket. I'm just going to shade everything in between. At 3, I'm going to put a bracket. And then I'm going to shade everything to the right.